Hello, wonderful stargazers. Welcome back to another journey through the cosmos, where tonight we're going to explore something that might keep you awake for just a few minutes before it gently carries you into the most peaceful sleep. Because what we're about to discuss is both thrilling and humbling in equal measure. Imagine standing at the edge of existence itself, looking out at places so strange, so utterly unreachable, that even our most ambitious dreams of space travel could never take us there. Not because our technology isn't advanced enough, not because we haven't built the right spaceship yet, but because the fundamental laws of physics themselves have drawn a line in the cosmic sand and whispered, "No further." Tonight we're going to visit 7 of the strangest places in the universe that humans can never reach. And by the end of our journey, you'll understand why some doors in the cosmos are locked not with keys, but with the very fabric of reality itself. If you're ready to drift through the impossible tonight, go ahead and give this video a like. And if you haven't already, subscribe and turn on notifications, because we have so many more cosmic mysteries to explore together. Trust me, you won't want to miss what's coming. Let me start with something that might surprise you. When Neil Armstrong stepped onto the moon in 1969, he traveled roughly 240,000 miles from Earth. It was the farthest any human being had ever ventured from home, and it remains one of our species' greatest achievements. But here's what's remarkable in cosmic terms. Armstrong barely left the front porch. The moon is so close to Earth that if you could drive there in your car at highway speeds, it would take you about 6 months. Mars, our next ambitious destination, would take you around 70 years of nonstop driving. But the places we're going to explore tonight, some of them are so impossibly distant, so fundamentally unreachable, that even traveling at the speed of light for billions of years wouldn't get you there. And others are so strange that distance isn't even the right way to think about them. You see, there's an important distinction we need to make right from the start. And it's a distinction that changes everything. There are places in the universe that are unreachable because of technology. Maybe we haven't figured out how to build a fast enough spaceship, or we haven't solved the problem of keeping humans alive for centuries-long voyages through the void. These are engineering problems, difficult certainly, but theoretically solvable given enough time and ingenuity. But then there are places that are unreachable because of physics itself. Places where the laws of nature have erected barriers that no amount of technological advancement can overcome. It's the difference between not having built the right ladder yet and discovering that the thing you're trying to reach exists in a dimension where ladders simply cannot exist. Think of it this way. Right now, you're lying in bed, probably comfortable, probably warm, breathing air that's just right for your lungs. But there are environments on Earth that would kill you instantly. The bottom of the Mariana Trench would crush you under pressures exceeding 15,000 pounds per square inch. The summit of Mount Everest without oxygen would suffocate you in minutes. The core of a nuclear reactor would irradiate your cells beyond any hope of survival. Yet, we've built submarines that reach the deepest trenches. Climbers summit Everest regularly. We've designed robots that can work inside reactor cores. Human ingenuity, given enough time and resources, can find ways to visit or at least study almost any extreme environment on our planet. But the places we're exploring tonight operate on an entirely different level of impossibility. They're not just hostile to human life. They're hostile to the very concept of reaching them. Some of these places are racing away from us faster than light itself can travel. Others exist at scales so small that the concept of space breaks down entirely. One of them would crush you not into a pancake, but into a stream of atoms, and then crush those atoms into their component particles, and then crush those particles into something physics doesn't even have proper words for yet. These aren't just dangerous places. They're places where the universe has essentially hung up a sign that says, "Reality does not function here," in ways you can survive or even comprehend. Let me give you a number that should make you pause. The observable universe, everything we can potentially see with our most powerful telescopes, everything that light has had time to reach us from, since the Big Bang spans about 93 billion light years across. That's already an incomprehensibly vast distance. 1 light year is about 6 trillion miles. Multiply that by 93 billion, and you get a number so large it loses all meaning to our human brains. But here's what keeps astronomers up at night. The observable universe is just a tiny fraction of the total universe. Based on our current understanding of cosmic inflation and the expansion of space, roughly 94% of the total universe lies beyond what we can ever observe. Not what we can observe with today's telescopes, but what we can ever observe even in principle, even if we had infinite time and perfect instruments. This cosmic horizon exists because the universe is expanding, and in the farthest reaches of space, it's expanding faster than light can travel through it. Imagine you're on a treadmill trying to walk forward, but the treadmill is moving backward faster than you can walk. You could walk forever and never make progress. That's what light from the most distant parts of the universe faces. It's traveling toward us at 186,000 miles per second, the fastest speed possible. But the space between us and those distant regions is stretching so rapidly that the light is actually getting farther away from us with each passing moment. Those regions are beyond our cosmic horizon, and they always will be. The universe has locked away 94% of itself, and it's thrown away the key. Now, you might be thinking, but wait, if we can't see it or reach it, how do we know it's there? And that's exactly the right question to ask. We know about this unreachable universe the same way a sailor in ancient times might have known there was more ocean beyond the horizon, even though he couldn't see it. The mathematics of general relativity. Einstein's theory of how gravity and space-time work together doesn't just describe what we can see. It makes predictions about what must exist beyond our view. And every test we've ever done of general relativity, from GPS satellites to observations of black holes, has confirmed that Einstein's equations are stunningly accurate. When those same equations tell us about regions of space we can never reach, we have excellent reasons to trust them. But cosmic horizons are just one category of unreachable places. Tonight we're going to explore 7 distinct types of impossibility, each one strange in its own unique way. We'll venture to the edge of a black hole, where space-time itself becomes so warped that escape is literally impossible, where reaching something means you can never return to tell anyone about it. We'll shrink down to the Planck length, a scale so microscopically tiny that the smooth fabric of space-time we experience every day dissolves into a seething quantum foam, where causality itself becomes uncertain. We'll journey to the heart of a neutron star, where matter is compressed so densely that a teaspoon of it would weigh more than Mount Everest, and where the very atoms that make up your body would cease to exist as recognizable structures. We'll also visit somewhere quite different, the Boötes Void, a region of space so empty, so profoundly devoid of galaxies and stars, that if Earth were somehow transported there, our night sky would be almost completely black. No stars, no Milky Way, no neighboring galaxies, just a few dim, distant points of light, separated by distances so vast, they make our cosmic loneliness seem almost cozy by comparison. It's unreachable, not because of any physical barrier, but because of sheer incomprehensible distance. And we'll explore a place that might not even exist, white holes, the theoretical time-reverse twins of black holes that mathematics says could be real, but that the universe seems to have decided against creating. Each of these places teaches us something profound about the nature of reality. They're not just exotic destinations in some cosmic travel guide. They're boundaries that define what's possible, landmarks that show us the edges of the map. In ancient times, cartographers would mark unexplored regions of their maps with phrases like, "Here be dragons." But the places we're exploring tonight have warnings far more fundamental, "Here be the limits of existence itself." And here's what I find beautiful about these unreachable places. They remind us that the universe is under no obligation to be fully accessible to us. We live in an era where we can order products from across the world and have them arrive at our doorstep in days where we can video, call someone on the opposite side of the planet, where information flows so freely that it's easy to forget that boundaries exist at all. But the cosmos operates on different rules. It has secrets it will never share places. It will never allow us to visit mysteries that will remain mysterious, not because we haven't been clever enough, but because they exist in regimes where our normal concepts of visiting or knowing simply don't apply. There's a humility in that realization, but also a strange comfort. The universe is vast beyond our wildest dreams, strange beyond our capacity to imagine, and filled with places we can never go. And yet, here we are, conscious beings capable of understanding these boundaries, of mapping the edges of reality, even when we can never cross them. We may never touch the quantum foam or survive the interior of a neutron star, but we can understand them. We can write the equations that describe them. We can peer at them through the lens of mathematics and physics and glimpse their nature even if we can never experience them directly. So, tonight as you settle into your pillow and let your breathing slow, we're going to take a journey to the boundaries of existence. We're going to explore places that are unreachable, not because we haven't tried hard enough, but because the fundamental architecture of reality has placed them beyond our grasp. We're going to stand at the edge of black holes and quantum realms, neutron stars, and cosmic voids, and we're going to understand why some doors in the universe are meant to remain closed. And who knows? By the time we reach the end of our journey, you might find that understanding the unreachable is its own kind of reaching. That knowing the boundaries of the possible is itself a profound achievement, one that connects you to the deepest truths about the cosmos and your place within it. So, take a deep breath. Let your body relax into the mattress. And let's begin our journey to the first of these impossible places, the event horizon of a black hole, where space and time trade places, and where the normal rules of cause and effect break down so completely that even light cannot escape. It's a place where reaching takes on an entirely new meaning, and where the boundary between reachable and unreachable is drawn with absolute unforgiving precision. There's a sphere surrounding every black hole where time itself begins to die. Cross that invisible boundary, and every law of physics you've ever learned gets rewritten. Light, the fastest thing in existence, becomes trapped like a fly in amber. Cause and effect start flowing backward. And if you were somehow conscious enough to witness, it would experience something so utterly alien that human language doesn't have adequate words to describe it. This boundary has a name, the event horizon. And once you cross it, the universe itself conspires to ensure you can never ever come back. Let's start with what a black hole actually is, because the popular image of a cosmic vacuum cleaner sucking up everything around it isn't quite right. A black hole is what remains after a massive star, at least 8 to 10 times the mass of our sun, exhausts all its nuclear fuel and collapses under its own gravity. For millions of years, that star fought a delicate battle between the inward crush of gravity and the outward pressure of nuclear fusion happening in its core. Fusion creates energy, and energy creates pressure, and that pressure pushes outward against gravity's relentless inward pull. It's a standoff that can last for eons, but eventually, inevitably, the fusion fuel runs out. And when it does, gravity wins. Catastrophically. The collapse happens faster than you can blink. The star's core, an object that might have been thousands of miles across, compresses down to a point of literally infinite density called a singularity. All that mass, all those atoms that once made up a star, larger than our entire solar system, crushed into a space smaller than the period at the end of this sentence. The outer layers of the star rebound off this incomprehensibly dense core and explode outward in what we call a supernova, one of the most violent events in the universe. But the core just keeps collapsing, getting denser and denser, until it tears a hole in the fabric of space-time itself. And that hole that wound in reality is what we call a black hole. But here's what's crucial to understand. A black hole isn't really a hole at all, and it's not really black. It's an object, a real physical thing, with mass and gravity, just like the Earth or the Moon. It's black because nothing, not even light, can escape from inside its event horizon to reach our eyes. And the event horizon itself isn't a physical surface you could touch like the surface of a planet. It's a mathematical boundary, a point of no return, the place where the escape velocity equals the speed of light. Think about escape velocity for a moment. On Earth, if you want to throw a ball so high that it never comes back down, you need to throw it at about 25,000 miles per hour. That's Earth's escape velocity. On the Moon, with its weaker gravity, the escape velocity is only about 5,300 miles per hour. On Jupiter, with its massive bulk, you'd need to reach nearly 134,000 miles per hour. Now, imagine an object so dense with gravity so powerful that the escape velocity exceeds 186,282 miles per second, the speed of light. That's what a black hole is. And the event horizon is the distance from the singularity where that happens. For a black hole with the mass of our sun, the event horizon would have a radius of about 1.9 miles. That's it. All the sun's mass compressed so densely that you'd need to be within 1.9 miles of the center for light itself to be trapped. For a supermassive black hole like Sagittarius, A star, the one at the center of our Milky Way galaxy, with a mass of about 4 million suns, the event horizon radius is roughly 7.3 million miles. These are real numbers calculated from real observations of how stars and gas orbit around these invisible monsters. Now here's where things get truly strange. Let's imagine you had a spaceship somehow capable of approaching a black hole, and you decided for reasons we won't examine too closely to fall in. Your friend agrees to stay safely outside the event horizon, watching you through a powerful telescope. What you experience and what your friend sees would be so dramatically different that you might as well be living in two separate universes. From your friend's perspective, watching from a safe distance, something bizarre happens as you approach the event horizon. You start to slow down, not because you're firing your rockets or putting on the brakes, but because time itself is slowing down for you relative to your friend. This isn't science fiction. This is a consequence of Einstein's general relativity verified by countless experiments. As you get closer to the event horizon where gravity becomes more intense, time dilation becomes more extreme. Your friend watches as your spacecraft inches closer and closer to that boundary, but never quite seems to reach it. You're moving slower and slower, like a film being played at a fraction of its normal speed. And the light from your spacecraft gets redder and redder, stretched out by the intense gravitational field into longer and longer wavelengths, a phenomenon called gravitational redshift. Eventually, your friend sees you frozen at the event horizon, dimmer and dimmer, redder and redder, until finally you fade from view, entirely taking infinite time from their perspective to actually cross the boundary. But from your perspective, falling toward the black hole, nothing special happens at the event horizon at all. There's no wall, no barrier, no sign that says, you are now entering a region from which escape is impossible. You simply pass through probably without even noticing the exact moment it happens. Time feels normal to you. Your watch ticks along normally. Your heart beats normally. To you, crossing the event horizon might take only a few minutes or even seconds, depending on the size of the black hole. This is one of the most mind-bending aspects of relativity. Your subjective experience of time remains unchanged, even as an outside observer would say, time has stopped for you entirely. Once you're inside the event horizon, something even stranger happens, something that should make you pause and really think about what space and time actually are. Inside the event horizon, the roles of space and time swap. Outside the event horizon, you can move freely through space. You can go left or right, forward or backward, up or down. But you cannot move through time in any direction except forward. Time only flows one way. Inside the event horizon, it's the opposite. The direction toward the singularity becomes time-like rather than space-like. Moving toward the singularity isn't a choice anymore. It's as inevitable as tomorrow. You can no more avoid falling into the singularity then you can avoid aging forward in time right now. You could fire your rockets with infinite power in the opposite direction, and it wouldn't matter. The singularity is in your future, and your future is the one direction you cannot help but travel toward. This is what makes the event horizon truly unreachable from the other direction. It's not that there's a force field pushing you back, it's that back becomes a direction in time rather than space, and you cannot travel backward in time. Trying to escape from inside a black hole is like trying to return to yesterday. The structure of space-time itself forbids it. But let's talk about what actually happens to your body as you fall, because this is where black holes reveal their truly hostile nature. There's a phenomenon with a darkly whimsical name, spaghettification. The formal term is tidal disruption, but spaghettification captures the visual reality of what happens much more effectively. Imagine you're falling feet first toward a black hole. Your feet are closer to the singularity than your head, and therefore they experience stronger gravity. How much stronger? Well, that depends on the size of the black hole. For a stellar mass black hole, one formed from a collapsed star, the difference in gravitational pull between your head and feet, even when you're still outside, the event horizon would be enormous. Let's say the black hole has 10 times the sun's mass and you're just crossing the event horizon. The gravitational force on your feet might be thousands of times stronger than on your head. Your body would be stretched lengthwise like taffy. At the same time, you'd be compressed from the sides, squeezed as the geometry of space-time funnels you toward the singularity, stretched vertically compressed, horizontally, until you literally become a stream of atoms, then a stream of particles, and finally a stream of quantum information flowing inexorably toward the center. For smaller black holes, this would happen well before you reach the event horizon. You'd be torn apart in the most spectacular and horrifying way imaginable long before you could cross the point of no return. But here's a strange mercy for supermassive black holes, the ones millions or billions of times the mass of the sun. The event horizon is so far from the singularity that the tidal forces at the event horizon are relatively gentle. You could potentially cross the event horizon of a supermassive black hole without being instantly destroyed. You might survive for minutes, maybe even longer, falling through the darkness inside, before the tidal forces eventually grew strong enough to tear you apart closer to the singularity. What would you see during those final minutes? Strangely, you'd see the universe, light that fell into the black hole before you light, that's been spiraling around inside, bouncing through the curved space-time, would still be visible. You might see distorted images of the outside universe light that's been redshifted and bent into strange shapes by the extreme curvature of space. Some physicists have suggested you might even see multiple images of the universe at different points in its history, light from different eras all arriving at your eyes simultaneously, because of how the black hole warps the flow of time. It would be the most spectacular and terrifying light show in existence, and you'd be the only one who could ever witness it, because no information about what you're seeing could ever get back out to tell anyone else. Now, at the center of the black hole, there's the singularity. This is where our physics breaks down completely. A singularity is a point of infinite density where all the mass of the black hole is concentrated into zero volume. Infinity appears in the equations. Infinite density, infinite curvature of space-time, infinite tidal forces. And when infinity appears in physics equations, it's usually a sign that something is wrong with the equations, that they're being pushed beyond their domain of applicability. Physicists don't really believe the singularity is literally a point of infinite density. Most think that when you get down to scales approaching the Planck-length quantum effects that we don't yet understand would take over and prevent the formation of a true mathematical singularity. We'd need a theory of quantum gravity, a way to merge Einstein's general relativity with quantum mechanics to really understand what happens at the center of a black hole. But we don't have that theory yet. It's one of the great unsolved problems in physics. So the singularity remains a mystery, a place where our understanding of reality simply stops. There's another deeply puzzling aspect to black holes that's troubled physicists since the 1970s. It's called the black hole information paradox, and it goes to the heart of what we mean by reality itself. In quantum mechanics, information is never destroyed. If you know the precise state of a system at one time, you can in principle calculate its state at any other time, forward or backward. Information is preserved. But what happens to information that falls into a black hole Stephen Hawking discovered in 1974? That black holes aren't entirely black. They emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. Over vast stretches of time, this radiation carries energy away from the black hole, causing it to gradually evaporate. Eventually, given enough time, the black hole would disappear entirely. But here's the problem. Hawking radiation appears to be completely thermal, completely random, carrying no information about what fell into the black hole. So, if you threw an encyclopedia into a black hole and then waited for the black hole to evaporate via Hawking radiation, the information in that encyclopedia would be gone, destroyed, erased from the universe. This violates a fundamental principle of quantum mechanics. Information can't just disappear. The paradox has spawned decades of theoretical work, with proposals ranging from the idea that information is somehow encoded in the Hawking radiation in ways too subtle for us to detect, yet to more radical suggestions that the event horizon itself isn't quite what we think it is, that it's fuzzy or has structure at the quantum level that preserves information. The debate continues, and it's one of those beautiful moments in science where two of our best theories, quantum mechanics and general relativity, seem to contradict each other at a fundamental level, suggesting that we're missing something deep and important about how reality works. Can you imagine being part of the research trying to solve that? Can you picture the intellectual excitement of knowing that there's something profound we don't understand yet about the most extreme objects in the universe? So, when we say the interior of a black hole is unreachable, we mean it in multiple senses. It's unreachable because once you cross the event horizon, the structure of space-time prevents you from leaving. It's unreachable because no information can escape to tell us what's inside. It's unreachable because the extreme conditions would destroy any structure, any complexity, any organized matter that fell in. And it's unreachable to our current understanding because the physics that governs the singularity lies beyond our present theories. Black holes are places where the universe itself has said, beyond this point, the normal rules no longer apply. They're not just objects in space. They're boundaries in the fabric of reality, places where space and time themselves become so distorted that our everyday concepts of past, future, inside, and outside lose their meaning. They're the universe's ultimate keep-out sign, enforced not by walls or forces, but by the fundamental geometry of existence itself. And yet, paradoxically, we understand them better than almost any other extreme environment in the cosmos. We've detected gravitational waves from colliding black holes. We've photographed the shadow of a supermassive black hole in the center of the M87 galaxy. We've watched stars orbit the black hole at the center of our own galaxy, with such precision that we've measured its mass to exquisite accuracy. We've verified Einstein's predictions about how black holes warp space and time. We understand the mathematics of event horizons and singularities, even if the singularities themselves remain mysterious. Black holes are unreachable, but they're not unknowable. And that distinction between what we can visit and what we can understand becomes even more important as we move to our next destination. Because now, we're going to venture to places so distant that even light from them will never reach us, regions of the universe racing away from us faster than physics permits anything to travel. We're going to explore the cosmic horizon and discover that 94% of the universe is not just unreachable, but unseeable, unknowable forever, beyond the boundary of what can ever be observed. The universe is larger and stranger than most people realize, and the vast majority of it has already slipped beyond any possibility of contact or communication, vanishing into the expanding void like ships disappearing over an ever-growing horizon. Let's see why distance that most familiar of concepts can become its own form of impossibility. Right now, at this very moment, there are galaxies racing away from us so fast that their light will never ever reach Earth. Not in a million years, not in a billion, not ever. These galaxies exist. They're real, filled with stars and planets, and perhaps even civilizations looking up at their own night skies. But they might as well be in another universe entirely, because the space between us and them is stretching faster than light can travel through it. The universe has a horizon just like the ocean does, but unlike a ship that disappears over Earth's horizon and could theoretically sail back, these galaxies are disappearing forever, slipping beyond a boundary that even light itself cannot cross. Picture yourself standing on a beach watching the sun set over the ocean. You can see perhaps 12 to 15 miles to the horizon before the curve of the Earth hides everything beyond. Everything past that line exists, of course. There are ships out there, islands, other continents, but you simply cannot see them from where you're standing because the Earth's surface curves away. Now, imagine that the ocean itself is growing, that the water between you and those distant ships is expanding, creating new ocean between you and them. And imagine it's expanding so fast that even if those ships sailed toward you at the fastest speed physically possible, they'd actually be getting farther away. The new ocean appearing between you is outpacing their journey. That's essentially what's happening with distant galaxies in our universe, except instead of water, it's space itself that's expanding. This might sound like science fiction, but it's based on one of the most well-tested discoveries in astronomy. In 1929, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made an observation that changed our understanding of the cosmos forever. He was studying galaxies, measuring their distances and their velocities, and he noticed something peculiar. The farther away a galaxy was, the faster it appeared to be moving away from us. And it wasn't just a few galaxies. It was all of them. Every galaxy he observed was receding, and the relationship was mathematical, precise, elegant. Double the distance, double the recession velocity. At first, this might seem to suggest that we're at the center of the universe, that everything is fleeing from us specifically, but that's not what's happening at all. The universe isn't expanding into anything, and there's no center to the expansion. Space itself is expanding everywhere, simultaneously carrying galaxies along with it, like raisins in a rising loaf of bread. If you were standing on any other galaxy, you'd see exactly the same thing we see. All the other galaxies would appear to be moving away from you, with more distant ones moving faster. It's not that galaxies are flying through space away from us. It's that the space between us and them is growing. Now Hubble's observations only covered relatively nearby galaxies, cosmically speaking. The most distant galaxies he could see were perhaps a few 100 million light-years away, and their recession velocities were substantial, but nowhere near the speed of light. But as telescopes improved and we could see farther into the universe, we discovered something remarkable and slightly unsettling. The expansion isn't slowing down, as you might expect from the mutual gravitational attraction of all the matter in the universe. It's accelerating. Distant galaxies are receding faster and faster. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that earned them the Nobel Prize and fundamentally altered our understanding of the universe. They found that the expansion of the universe is accelerating, driven by something we call dark energy. We don't know what dark energy is. We don't know why it exists. We can't see it, touch it, or detect it directly. We only know it exists because of its effect. It's causing the expansion of space to speed up. And dark energy isn't some minor component of the universe. It makes up roughly 68% of all the energy in the cosmos. Dark matter, the mysterious substance that provides extra gravity to hold galaxies together, makes up another 27%. Everything we can see, all the stars and planets and gas and dust, all the normal matter that makes up you and me, and everything we've ever touched amounts to less than 5% of the total universe. This accelerating expansion has profound consequences for what we can observe and what we can potentially reach. Let me explain with some numbers that should make you pause and really think about the scale of what we're discussing. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light years. Now, you might immediately wonder, how can we see objects 46.5 billion light years away if the universe is only about 13.8 billion years old? Shouldn't light have only had time to travel 13.8 billion light years? This is one of the most common misconceptions about cosmology, and it's worth taking a moment to clear it up. When we look at a distant galaxy, we're not just seeing how far the light has traveled. We're seeing an object that was much closer to us when it emitted that light, but has since moved farther away due to the expansion of space. The light from the most distant galaxies we can see has been traveling toward us for nearly 13.8 billion years, almost since the beginning of the universe. But during that time, those galaxies have been carried away by the expansion of space. By now, they're much farther away than 13. 8 billion light years. That's why the observable universe is larger than the age of the universe would suggest. But here's where it gets really interesting and a little bit melancholy. The observable universe is not the same as the total universe. In fact, based on our best models of cosmic inflation and expansion, the observable universe is just a tiny bubble in a vastly larger cosmos. And most of that larger cosmos is already beyond our cosmic horizon, meaning light. From those regions will never reach us no matter how long we wait. Let me give you a specific example to make this concrete. There's a galaxy called GNZ, 11 discovered by the Hubble Space Telescope in 2016. When its light left that galaxy, the universe was only about 400 million years old, making it one of the most distant galaxies ever observed. The light we're seeing from GNZ 11 has traveled for approximately 13.4 billion years to reach us. But because of the expansion of space during that journey, GNZ 11 is now roughly 32 billion light years away from us. And here's the crucial point. GNZ 11 is receding from us at a velocity far exceeding the speed of light. Not because the galaxy itself is moving through space that fast, which would violate special relativity, but because the space between us is expanding. General relativity has no speed limit on how fast space itself can expand. Now, when we say something is receding faster than light, we need to be precise about what that means. If you tried to send a signal to GNZ 11 right now, a beam of light carrying a message that light would begin its journey traveling at 186,282 miles per second, as all light does. But the space between us and GNZ 11 is expanding so rapidly that the light, despite traveling at its maximum speed, would actually be getting farther from GNZ 11 with each passing moment. The expansion would overpower the light's motion. Your message would never arrive, ever. You could wait trillions of years, and it wouldn't matter. The photons carrying your message would be swimming against a current too strong to overcome, trapped in a region of space that can never make contact with GN-Z11's region. This defines something called the Hubble sphere, or the cosmic event horizon. It's the boundary beyond which the recession velocity of space equals the speed of light. Objects beyond this boundary are fundamentally unreachable and unseeable. Not unreachable in the sense that we haven't built a fast enough spacecraft. Unreachable in the sense that no signal we could ever send, even traveling at the ultimate speed limit of the universe, could ever reach them. The current radius of this cosmic event horizon is estimated to be about 16 billion light years. Every galaxy beyond that distance is lost to us. And it gets worse. Because the expansion is accelerating due to dark energy, The cosmic event horizon is actually shrinking over time in terms of which galaxies remain accessible. Galaxies that are currently within our observable universe, galaxies we can see right now, are gradually crossing over that horizon and disappearing from view forever. It's like standing on a beach as the tide rushes out, watching the shoreline recede farther and farther, except the tide never comes back in. It just keeps going, and everything beyond it is gone. Let's do some math to understand just how much of the universe we're talking about. If we assume that the universe is infinite, which many cosmologists believe based on measurements of its curvature, then the fraction of the universe we can observe is exactly zero. Infinity divided by any finite number is still infinity. But even if we assume the universe is merely extremely large but not infinite, say if it's 1,000 times larger than our observable bubble, then we can see only about 1/billionth of what exists. Current estimates based on cosmic inflation theory suggest that the total universe might be at least 10 to the power of 23 times larger than the observable universe. That's a 1 followed by 23 zeros. If that's true, then the fraction of reality we can observe is incomprehensibly small. Approximately 94% of the galaxies that exist in the total universe are already beyond our cosmic horizon. They were never visible to us, and they never will be. Their light racing toward us at the speed of light since the beginning of time has not and will not ever reach Earth, because the expansion of space has carried them beyond the boundary. And every day more galaxies slip over that edge. In the very distant future, tens or hundreds of billions of years from now, the accelerating expansion will have carried nearly every galaxy beyond our cosmic horizon. An observer on Earth, if Earth still exists, and if there are any observers left, would look out at the night sky and see almost nothing, the Milky Way and perhaps a few dozen galaxies in our local group that are gravitationally bound to us tightly enough to resist the expansion and beyond that darkness. The rest of the universe, all those trillions of galaxies will have vanished, leaving future astronomers with an almost empty cosmos to study. This has a rather poignant implication. We live in what might be called the golden age of cosmology. We can see enough of the universe to understand its large-scale structure, its expansion, its evolution. We can study distant galaxies and learn about the early universe. But this won't always be true. Eventually, the evidence for the Big Bang, for the expansion of space, for the existence of other galaxies will literally disappear as those galaxies move beyond our horizon. Future civilizations, if any exist, might look at the sky and conclude they live in a small, static, eternal universe, containing only their local group of galaxies surrounded by infinite darkness. They'd be wrong, but they'd have no evidence to correct their misconception, because the expansion will have hidden all the evidence. There's something deeply unsettling about this, isn't there? The idea that the universe is not only vast beyond comprehension, but that most of it is forever inaccessible, forever unknowable. We can write the equations that describe these distant regions. We can calculate what the physics must be like there. But we will never observe them, never confirm our theories about them, never know for certain what wonders or horrors might exist in that unreachable 94%. And here's perhaps the most philosophically challenging aspect of this cosmic horizon. It's not like a black hole's event horizon where we understand the exact physics that makes crossing it impossible. With the cosmic horizon, there's nothing physically preventing us from going there, no barrier we'd encounter, no force field pushing us back. If we somehow had a spacecraft that could travel at close to the speed of light and we pointed it at a galaxy that's currently just beyond our horizon, we could in principle start the journey. The problem is that the goal is moving away faster than we can travel. We'd be like a runner on a treadmill, expending infinite energy to chase a finish line that recedes forever. Can you imagine the frustration? Can you picture the tragedy of knowing something exists, but being fundamentally unable to reach it? Not because of any limitation in your technology, but because the very geometry of space-time forbids the journey. But let's think about this from another angle. What does it mean for something to exist if it can never interact with us in any way? Philosophers and physicists have debated this question for centuries in various forms, and the cosmic horizon gives it a new urgency. Those galaxies beyond our horizon are real. They contain stars and planets. The laws of physics operate there just as they do here. But if no information can ever travel between them and us, if no signal we send can reach them, and no signal they send can reach us, do they exist for us in any meaningful sense? This touches on deep questions about the nature of reality itself. Is the universe only as large as the observable universe? Or does everything beyond our horizon exist just as fully as everything within it, even though we can never confirm it? Most physicists would say yes. Those distant regions exist just as much as the room you're lying in right now. They're part of the same space-time continuum, governed by the same laws. But there's no way to prove it. Those regions are not just unreachable, but in a very real sense, unknowable. There's a concept in relativity called the light cone, and it's useful for understanding what we mean by observable and reachable. Imagine a graph where time is the vertical axis and space is the horizontal axis. Your position right now is a point on that graph. Your past light cone is the region of space-time that could have sent light signals that reach you at this moment. Everything in your past light cone is observable to you, at least in principle. Your future light cone is the region of space-time that you could potentially send light signals to the region you could causally affect. Outside your light cone, both past and future, is a region that is neither observable by you nor influenceable by you. It's causally disconnected from your existence. The cosmic horizon represents the limit of our past, light cone extended infinitely into the future. Even if we wait forever, light from beyond that horizon will never reach us because the expansion is too fast. And those regions are also outside our future light cone. We cannot send signals there. We cannot affect them. They cannot affect us. For all practical purposes, and indeed for all physical purposes, they might as well not exist as far as we're concerned. Yet, here's the beautiful and slightly maddening part of this. We can calculate what's happening in those unreachable regions with reasonable confidence. Our equations don't care about observability. General relativity describes space-time everywhere, not just the parts we can see. We can predict that those distant regions contain galaxies and stars and planets, that they're governed by the same physics, that they're probably quite similar to the regions we can observe. We just can't verify any of it. It's knowledge without confirmation theory, without possible observation, a map of a territory we can never visit and never truly know exists. This is very different from the black hole scenario we discussed earlier. With black holes, we understand exactly why escape is impossible. The geometry of space-time inside the event horizon points all paths toward the singularity. With the cosmic horizon, it's subtler. There's nothing stopping us from going there in principle. If we could somehow travel faster than the expansion rate, we could reach those distant galaxies. But we can't. The expansion rate exceeds the speed of light, and the speed of light is an absolute limit on how fast any object with mass can travel through space. So, the cosmic horizon is unreachable not because of a barrier, but because of a competition between velocities that we cannot win. And this brings us to a rather sobering thought about the future. Because the expansion is accelerating, the cosmic horizon is effectively shrinking. More and more galaxies are slipping beyond it every day. In about 150 billion years, give or take, almost every galaxy beyond our local group will have disappeared beyond the cosmic horizon. The universe will have expanded so much that the night sky for any observers that might exist then will be nearly empty. The Milky Way, Andromeda, and a few dozen smaller galaxies all gravitationally bound together in what astronomers call the local group will be all that's visible. Everything else, every other structure in the cosmos, will have been carried away by the expansion into unreachable, unseeable distance. This scenario, sometimes called the heat death of the universe, or the Big Freeze, is our current best prediction for the ultimate fate of the cosmos. The stars will eventually burn out. Black holes will evaporate via Hawking radiation. over time scales so vast they make billions of years look like an eye blink. And in the end, if you could somehow survive to see it, you'd find yourself in a cold, dark, empty universe, the few remaining structures separated by distances so vast that they might as well be alone in existence. It's a lonely vision, but it's what the mathematics tells us. Of course, predictions about the far future of the universe are always tentative. We're extrapolating our current understanding of physics across unimaginable stretches of time. Perhaps there are processes we don't understand yet that could change the picture. Perhaps dark energy itself will evolve over time, changing its effect on the expansion. Perhaps quantum fluctuations or other exotic phenomena will create new structures in the distant future. We simply don't know. But based on everything we currently understand, the universe is headed toward a state of maximum expansion, maximum entropy, and profound isolation. So, when we talk about unreachable places in the universe, we have to include this vast majority of reality that has already slipped beyond our cosmic horizon, carrying with it untold billions of galaxies, septillions of stars, and who knows how many worlds and civilizations. They exist, they're real, but they're as inaccessible to us as yesterday is to someone trying to travel backward in time. The expansion of space has built a wall that no technology, no matter how advanced, can overcome, because the wall is built into the structure of space-time itself. It's a humbling realization, but also a clarifying one. It reminds us that the universe doesn't care about our desire to explore it. It operates according to laws that sometimes permit exploration and sometimes forbid it. And we're subject to those laws, just like everything else. We can understand the unreachable regions. We can describe them with mathematics. We can theorize about them, but we can never go there, and we can never see them. They're beyond the edge of the possible, hidden not by a lack of technology, but by the fundamental geometry of the expanding cosmos. And yet, as vast and unreachable as these cosmic distances are, they're still comprehensible in a way. They're getting farther, but we can at least conceive of the distance involved. Our next destination takes us to a different kind of unreachable place, not defined by distance at all, but by scale. We're about to shrink down to the smallest possible size, to a realm where the very concept of space begins to dissolve into quantum foam, where the smooth fabric of reality we experience every day breaks apart into a seething, bubbling chaos. We're going to explore the Planck length and discover that just as there's a largest scale beyond which we cannot see, there's also a smallest scale below, which we cannot go a fundamental limit built into the nature of space and time themselves. There's a size so impossibly tiny that the universe itself seems to panic at the thought of anything smaller. At this scale, space and time don't behave like the smooth, continuous fabric we experience in our everyday lives. Instead, they bubble and froth like boiling water, with tiny wormholes appearing and disappearing, particles popping into and out of existence, and the very notion of here and there losing all meaning. This scale has a name, the Planck length, approximately 1.6 times 10 to the power of minus 35 meters. And it represents not just the smallest distance we can measure, but quite possibly the smallest distance that can exist. Let me start by giving you some perspective on just how small we're talking about. Take a hydrogen atom, the simplest and smallest atom in existence. Its diameter is roughly 1/10 billionth of a meter, or 10 to the power of minus 10 meters. That's already incomprehensibly tiny. You could line up about 10 billion hydrogen atoms across the distance of 1 meter. Now, the Planck length is to a hydrogen atom what a hydrogen atom is to a distance of about 100 million kilometers, roughly 2/3 the distance from Earth to the Sun. Try to wrap your mind around that for a moment. If you scaled a hydrogen atom up to the size of the observable universe, the Planck length would only grow to about the size of an average tree. The Planck scale is so fantastically small that it exists in a realm completely divorced from anything we can directly experience or even properly imagine. This length was first calculated in 1899 by the German physicist Max Planck, the same Planck who gave us quantum mechanics and whose name now graces one of our most important physical constants. Planck wasn't trying to find the smallest possible distance. He was doing something much more fundamental. He was combining the three most important constants in physics to see what kind of natural units they would produce. He took the speed of light from Einstein's relativity, the gravitational constant from Newton's theory of gravity, and his own newly discovered quantum constant, and he mathematically combined them. What emerged were natural units of length, time, mass, and energy that didn't depend on human conventions like meters or seconds. These were units written into the fabric of nature itself. The Planck length that emerged from his calculation was approximately 1.616 times 10 to the power of minus 35 meters. Along with it came the Planck time, about 5.4 times 10 to the power of minus 44 seconds, which is how long it would take light to travel one Planck length. These numbers are so small, they defy intuition. The Planck time is to 1 second what 1 second is to about 10 million times the current age of the universe. In 1 second, more Planck time intervals pass than there have been seconds since the Big Bang multiplied by 10 million. It's a scale that makes atomic physics look positively gigantic by comparison. But here's what makes the Planck length so much more than just a very small number. It's not merely a measurement we haven't reached yet with our instruments. It appears to represent a fundamental limit, a boundary below which the very concept of distance stops making sense. And this limitation doesn't come from our technology or our measurement techniques. It comes from the principles of quantum mechanics and general relativity themselves, from the way uncertainty and gravity interact at extremely small scales. Let me explain why physicists believe nothing can be smaller than the Planck length and why trying to probe distances smaller than this leads to fundamental contradictions. It all comes down to Heisenberg's uncertainty principle, one of the bedrock discoveries of quantum mechanics. Heisenberg showed in 1927 that there's a fundamental limit to how precisely we can know certain pairs of properties simultaneously. The most famous example is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of our measuring instruments. It's built into the nature of reality itself at the quantum level. Now, if you want to measure something very small, you need to probe it with something that has a very short wavelength. In quantum mechanics, shorter wavelength means higher energy. This is why we build enormous particle accelerators like the Large Hadron Collider. We're accelerating particles to tremendous energies to give them very short wavelengths, so they can probe very small distances. The LHC can probe distances down to about 10 to the power of minus 19 meters, roughly 1/10,000th the size of a proton. That's incredibly small, but it's still about 10,000 trillion times larger than the Planck length. So, what happens if we try to build an even more powerful accelerator to probe even smaller distances? We'd need to concentrate more and more energy into a smaller and smaller region. And here's where general relativity enters the picture. Einstein's theory tells us that energy and mass curve space-time. Enough energy concentrated in a small enough region will curve space-time so severely that it creates a black hole. You can actually calculate the critical energy density, and what you find is remarkable and frustrating in equal measure. If you try to probe distances smaller than the Planck length, you'd need to concentrate so much energy in such a small region that you'd inevitably create a black hole, which would then hide whatever you were trying to measure behind an event horizon. The very act of trying to measure something smaller than the Planck length defeats itself. This is what physicists mean when they say the Planck length represents a fundamental limit. It's not that smaller distances definitely don't exist. It's that the laws of physics as we currently understand them prevent us from probing or even defining what smaller would mean. The uncertainty principle and general relativity conspire together to make the Planck scale a kind of resolution limit on reality itself, like the pixels on a screen. You can't have half a pixel. You can't zoom in further. The image is made of those discrete units, and that's as fine as the detail gets. But what exists at the Planck scale? What is the structure of space-time when you zoom in that far? This is where physics becomes almost poetic in its strangeness. The answer, according to our best theories, is something called quantum foam, and it's one of the most bizarre concepts in all of physics. Imagine the surface of the ocean on a calm day. From an airplane, it looks smooth and continuous, a placid blue expanse. As you get closer, you start to see waves, ripples, texture. Get close enough, and you see that the surface is never truly still. It's constantly moving, constantly shifting, with small waves and disturbances appearing and disappearing. Now imagine zooming in further down to the molecular level and seeing water molecules bouncing and jittering in their thermal motion. Quantum foam is like that, except it's space-time itself that's foaming and bubbling. At scales approaching the Planck length, the smooth four-dimensional fabric of space-time we experience in our everyday lives dissolves into a seething chaos. Virtual particles pop into existence in matter. Antimatter pairs borrow energy from the quantum vacuum, exist for infinitesimally brief moments, and then annihilate back into nothingness. Tiny wormholes might open and close, connecting different points in space-time for durations measured in Planck time units. The geometry of space itself fluctuates wildly, with the very notion of distance becoming fuzzy and probabilistic rather than definite. These aren't idle speculations. The existence of quantum fluctuations in empty space has been experimentally verified through phenomena like the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. If you place two uncharged metal plates very close together in a vacuum, they experience an attractive force pushing them together. This happens because the quantum vacuum between the plates can only support certain wavelengths of virtual particles, while the vacuum outside the plates can support all wavelengths. The pressure difference creates a measurable force. It's direct evidence that the quantum vacuum isn't empty at all, but filled with constantly fluctuating fields and virtual particles. At the Planck scale, these quantum fluctuations become so extreme that they dominate everything. The energy uncertainty in a Planck volume of space over a Planck time is enormous, large enough to create particle-antiparticle pairs, to curve space-time dramatically, perhaps even to create microscopic black holes that flash into and out of existence faster than light could cross them. Some physicists have described it as space-time boiling, every point in the universe engaged in a frenetic dance of creation and destruction, happening at such small scales and such brief durations that we never notice it in our everyday lives, just as you don't notice the individual molecules when you look at a glass of water. Can you imagine what it would be like if you could somehow perceive reality at this scale? If you could watch the quantum foam in action? Now here's where things get even more mind-bending. At the Planck scale, the distinction between space and time might break down entirely. In our normal experience, space and time are clearly different things. You can move freely through space in any direction, but you're dragged inexorably forward through time. But some approaches to quantum gravity, the still undeveloped theory that would unify general relativity and quantum mechanics, suggest that at the Planck scale, space and time might be equally fuzzy, equally uncertain, equally quantum. Time itself might be quantized, broken up into discrete Planck time chunks, rather than flowing smoothly. The idea of causality of one event following another might become ambiguous when the time interval between events is measured in Planck times. One of the most sophisticated attempts to describe physics at the Planck scale is something called loop quantum gravity. In this framework, space-time isn't infinitely divisible, but is instead made of discrete units, tiny loops of space-time, woven together into a network called a spin network. The nodes and links in this network represent quantum states of geometry, and the Planck length represents roughly the size of these fundamental units. In this picture space is literally quantized, made of discrete chunks, just as energy is quantized in quantum mechanics. You can't have a distance smaller than 1 unit, just as you can't have a fraction of a photon. Another approach, string theory, handles the Planck scale differently. In string theory, the fundamental entities aren't point particles, but tiny vibrating strings, and the characteristic size of these strings is set by the Planck length. Different vibration modes of the strings correspond to different particles. The string vibrating one way is an electron, another way is a photon, yet another way is a graviton, the hypothetical quantum of gravity. At distances much larger than the Planck length, these strings look like point particles, but at the Planck scale, their extended structure becomes important. The theory suggests that probing distances smaller than the string length doesn't reveal new structure, but instead just causes the strings to vibrate more energetically. Both loop quantum gravity and string theory remain highly speculative. Neither has been experimentally verified because testing predictions at the Planck scale is far beyond our current or foreseeable technology. The Large Hadron Collider, the most powerful particle accelerator ever built, can probe energies of about 10 to the power of 13 electron volts. To probe the Planck scale, we'd need energies of about 10 to the power of 28 electron volts, a factor of a quadrillion times more powerful. Building an accelerator that powerful is not just technologically infeasible, but physically impossible. Such a machine would require more energy than exists in the observable universe. So, the Planck scale remains for now, and likely forever, beyond the reach of direct experimental investigation. But let's think about what this means philosophically. We've discovered that there's a smallest possible scale to reality, a resolution limit below which the universe itself becomes undefined. This is profoundly different from how we thought about the world for most of human history. The ancient Greek philosophers debated whether matter could be divided infinitely, or whether there were ultimate indivisible units called atoms. Democritus and Leucippus argued for atoms. Aristotle argued for infinite divisibility. For more than 2,000 years, this debate continued shifting and evolving as our understanding grew. In the early 1800s, John Dalton revived the atomic theory on a scientific footing, suggesting that chemical elements were made of discrete atoms. By the early 1900s, we'd discovered that atoms themselves weren't indivisible, but contained electrons orbiting a nucleus. Then we found that the nucleus contained protons and neutrons. Then we discovered that protons and neutrons were made of quarks and gluons. Each time we thought we'd found the fundamental level, we discovered another layer underneath. But the Planck length suggests we're approaching the end of that particular journey. Not because we've found the smallest particles, though. Quarks and leptons seem to be truly fundamental, as far as we can tell. But because we've found the smallest distance. Even if there are structures smaller than quarks, even if reality has infinitely many layers of organization going down, we cannot probe below the Planck length. The universe has drawn a curtain and said, below this level, the rules you know no longer apply and you cannot pass. There's something both frustrating and beautiful about this limit. Frustrating because there's a fundamental boundary to knowledge, a place where physics admits it cannot answer questions about what's happening. Beautiful because it shows that the universe has an architecture that it's not just arbitrarily complicated all the way down, but has natural scales and boundaries written into its structure. Think about the scales of the universe we've explored so far in our journey. We talked about black holes and event horizons. We discussed galaxies racing away faster than light can chase them cosmic horizons beyond which we cannot see. And now, we've arrived at the opposite extreme, the smallest possible scale, where space and time themselves dissolve into quantum uncertainty. The universe has boundaries at both the largest and smallest scales, and we humans exist somewhere in between, able to understand both limits, even though we can never visit either one. Let me give you one final comparison to really hammer home how divorced the Planck scale is from our everyday experience. Take all the atoms in the observable universe. Current estimates put that number at about 10 to the power of 80 atoms. That's a 1 followed by 80 zeros, an incomprehensibly vast number. Now, consider a single hydrogen atom and compare it to the Planck length. The ratio between the size of a hydrogen atom and the Planck length is roughly 10 to the power of 25. Now, compare the size of the observable universe to the size of a hydrogen atom. That ratio is roughly 10 to the power of 35. So, in the hierarchy of scales, a hydrogen atom is actually much closer to the size of the entire observable universe than it is to the Planck length. The Planck scale is more foreign to an atom than the atom is to the cosmos itself. And at this unimaginably tiny scale in the seething quantum foam, where virtual particles blink in and out of existence in trillionths of a trillionth of a trillionth of a second, we've reached a place that is fundamentally unreachable. Not because we lack the right tools, though, we certainly do, but because the act of trying to reach it creates the very conditions that make it impossible to observe. It's a boundary written in the language of mathematics and physics, a place where the universe says not merely, "You cannot go here," but "here itself becomes undefined if you try too hard to specify what it means." Yet, even though we cannot visit the quantum foam, even though we cannot directly observe the Planck scale, we can describe it. We can write equations that tell us what must be happening there. We can understand the principles that govern it, even if we cannot see it directly. And that perhaps is the greatest achievement of human thought, to comprehend realms of reality that are forever beyond our direct perception, to map territories we can never visit, to understand boundaries we can never cross. From the smallest possible distances, we're now ready to venture to places defined not by smallness, but by extreme density. Our next stop takes us to the interior of a neutron star, where matter is compressed to densities that beggar the imagination, where a teaspoon of material weighs as much as a mountain, and where the very atoms that make up your body would be crushed into configurations so exotic that physicists had to borrow names from Italian cuisine to describe them. Let's explore what happens when gravity compresses matter beyond anything that exists anywhere else in the universe except inside black holes themselves. Imagine scooping up a single teaspoon of matter, just 5 milliliters, the amount you might use to stir your coffee. Now, imagine that teaspoon weighs 1 billion tons, not 1 billion pounds. 1 billion tons. That's roughly the weight of 150 Great Pyramids of Giza, or about 3,000 Empire State Buildings, all compressed into a volume you could hold in your hand if your hand weren't instantly vaporized by the attempt. This is the density of a neutron star, the most extreme form of matter that can exist in the universe without collapsing into a black hole. And the interior of these cosmic monsters represents a place so hostile, so utterly incompatible with anything we recognize as normal matter, that visiting one would be like trying to visit the surface of the sun while standing inside a hydraulic press being crushed by the weight of Mount Everest, all while being bombarded by radiation that would sterilize a planet. Neutron stars are born in violence, created in the final moments of massive stars' lives when they explode as supernovae. To understand what a neutron star is, we need to first understand what keeps normal matter from collapsing under its own weight. Right now, you're lying down, and the atoms that make up your body are maintaining their structure despite gravity trying to pull them together. What's holding them apart? It's not physical contact in the way we usually think of it. At the atomic level, atoms are mostly empty space. An atom's nucleus occupies only about 1 trillionth of the atom's total volume. The rest is occupied by electron clouds regions where electrons exist in quantum probability states. What keeps atoms from passing through each other is something called electron degeneracy pressure, a quantum mechanical effect that arises from the Pauli exclusion principle. This principle, discovered by Wolfgang Pauli in 1925, states that no two electrons can occupy the same quantum state simultaneously. When you try to squeeze atoms together, their electron clouds resist because the electrons have nowhere to go. They're already occupying all the available low-energy quantum states, and the Pauli exclusion principle forbids them from doubling up. This electron degeneracy pressure is what holds up white dwarfs, the stellar remnants left behind when stars like our Sun exhaust their nuclear fuel. A white dwarf is incredibly dense by everyday standards, with a mass comparable to the Sun compressed into a volume about the size of Earth. A teaspoon of white dwarf material weighs about 15 tons, roughly the weight of 2 elephants. But white dwarfs are fluffy and lightweight compared to neutron stars. When a star much more massive than the Sun, typically at least 8 to 10 solar masses, runs out of fuel, something far more catastrophic happens. The star's core, which has been fusing progressively heavier elements throughout its life, eventually produces iron. Iron is special because it's the most stable nucleus in terms of binding energy per nucleon. Fusing iron into heavier elements doesn't release energy, it requires energy. So, when a massive star's core turns to iron, fusion stops. Suddenly, there's no outward pressure to balance gravity's inward crush. The core collapses. In less than a second, a core that might have been thousands of miles across compresses down to a sphere perhaps 12 miles in diameter. The collapse is so rapid, so violent, that it releases more energy than the star emitted during its entire multi-million-year lifetime. And it releases it all in seconds. During this collapse, something extraordinary happens to the matter. The density becomes so extreme that electron degeneracy pressure, which held up the white dwarf, simply isn't strong enough anymore. The electrons are forced into the atomic nuclei, where they combine with protons in a process called electron capture, producing neutrons and neutrinos. The neutrinos, those ghostly particles that barely interact with anything, stream out of the collapsing core, carrying away enormous amounts of energy. But the neutrons remain packed together in the densest configuration that matter can achieve without becoming a black hole. What you end up with is an object about 12 to 15 miles across, containing between 1.4 and about 2.1 times the mass of the Sun. Let me repeat that for emphasis. A star's worth of mass compressed into a sphere you could fit inside a medium-sized city. The resulting density is approximately 400 trillion times denser than lead, or about the same density as an atomic nucleus. In fact, you can think of a neutron star as essentially a single giant atomic nucleus held together by gravity rather than the strong nuclear force containing something like 10 to the power of 57 neutrons. If Earth were compressed to neutron star density, it would be about 300 meters across, roughly the length of 3 football fields. The surface gravity of a neutron star is almost incomprehensible. At the surface, gravity is about 200 billion times stronger than on Earth. If you were standing on a neutron star, which you absolutely cannot do for reasons we'll explore, and you tried to jump, you'd need to achieve a velocity of about 100,000 kilometers per second. Roughly 1/3 the speed of light, just to get 1 millimeter off the ground. Your escape velocity would be roughly 150,000 kilometers per second, about half the speed of light. Drop a marshmallow from 1 meter above the surface, and by the time it hits, it would be traveling at about 2 million kilometers per hour, and would release energy equivalent to a small nuclear bomb upon impact. The gravitational pull is so intense that it warps space-time significantly, causing light to bend, and producing gravitational redshift. A photon climbing out of a neutron star's gravity well loses energy, its wavelength stretched by about 20 to 30%, making blue light look red by the time it escapes. But the surface, as exotic as it is only the beginning. Let's take a journey through the layers of a neutron star, starting from the outside and working our way in, and discover just how alien the interior becomes. The outermost layer, the atmosphere is only about a few centimeters thick, but contains temperatures of around 1 million degrees Celsius. Below that is the crust divided into an outer crust and an inner crust. The outer crust, extending down to about half a kilometer, consists of atomic nuclei arranged in a crystalline lattice similar in some ways to ordinary solid matter, except the nuclei are extraordinarily neutron-rich isotopes that would decay almost instantly under normal conditions. They're stable here only because of the immense pressure. The density in the outer crust ranges from about 1 million grams per cubic centimeter near the surface to about 100 trillion grams per cubic centimeter at the bottom. As you descend into the inner crust below, about half a kilometer depth, something strange begins to happen. The density increases to the point where neutrons begin to drip out of the nuclei, creating a sea of free neutrons flowing between the nuclear lattice. This region is sometimes called the neutron drip layer, and it extends down to about 1 kilometer depth. The physics here becomes increasingly exotic because you have both a crystal lattice of nuclei and a quantum fluid of neutrons coexisting in the same space, and their interactions produce phenomena that don't exist anywhere else in the universe. Then we reach what might be the strangest layer in the entire neutron star, the region where nuclear pasta forms. Yes, you read that correctly. Nuclear pasta. And no, I'm not making this up. This is actual terminology used by astrophysicists, and it describes one of the most bizarre states of matter ever theorized. At densities approaching that of nuclear matter, the nuclei in the crust begin to deform and merge in ways that depend on the local density and pressure. First, they might form cylindrical structures that physicists call spaghetti. Increase the pressure further, and these cylinders merge into flat sheets called lasagna. Compress even more, and you might get structures with cylindrical holes running through them, which physicists have whimsically named anti-spaghetti or bucatini after the hollow pasta. And if you go even deeper, you might find spherical bubbles in a dense neutron background, which some have called Swiss cheese phase, though that's not a pasta, so the naming convention breaks down slightly. These pasta phases aren't just theoretical curiosities. They might actually be the strongest material in the universe. Computer simulations suggest that nuclear pasta could have a breaking strength about 10 billion times greater than steel. It's so strong that vibrations in these structures might produce gravitational waves that we could potentially detect with future instruments. The pasta layer is thought to extend from about 1 to 2 kilometers below the surface down to the edge of the outer core. But as strange as nuclear pasta is, the true mystery lies deeper still in the core of the neutron star, and this is where our physics becomes genuinely uncertain. Below about 2 kilometers depth, you enter the outer core, where the density exceeds nuclear density, and normal atomic nuclei cease to exist entirely. What you have instead is a quantum fluid of neutrons with smaller amounts of protons and electrons mixed in. The neutrons are packed so tightly that they form what's called a degenerate Fermi gas, where quantum effects dominate and the neutrons essentially behave as a single quantum system rather than individual particles. In the outer core, the neutrons are likely in a superfluid state. A superfluid is a phase of matter that has zero viscosity, meaning it can flow without any friction whatsoever. If you could somehow create a vortex in superfluid neutron matter, it would spin forever without slowing down. Superfluidity emerges from quantum effects when particles cool below a critical temperature and begin to behave collectively, and the conditions inside a neutron star, despite the high temperatures, allow for this because of the extreme densities and quantum degeneracy. The protons in the outer core might also form a superconductor, a state where electrical resistance drops to zero. So you'd have a superfluid of neutrons coexisting with a superconducting fluid of protons, all at temperatures of millions of degrees, a combination that seems paradoxical but emerges naturally from the extreme quantum mechanics at play. And then there's the inner core, the absolute center of the neutron star. And this is where physics enters what I can only describe as educated speculation. We simply don't know what happens to matter at densities exceeding 2 to 3 times nuclear density. Our theories of the strong nuclear force which governs how quarks and nucleons interact become unreliable at these extreme conditions. Several possibilities have been proposed, each more exotic than the last. One possibility is that neutrons themselves break down their constituent quarks, becoming deconfined and forming what's called quark matter. In normal matter, quarks are always confined inside protons and neutrons. You never find a free quark wandering around by itself because the strong force binding them gets stronger with distance rather than weaker, making it impossible to separate them. But at the extreme densities in a neutron star's core, the quarks might be packed so tightly that the distinction between one neutron and another becomes meaningless, and you end up with a soup of free quarks, a state of matter called a quark-gluon plasma, or in its cold, dense form, strange quark matter. Strange quark matter is particularly interesting because it would contain not just the up and down quarks that make up normal protons and neutrons, but also strange quarks, a heavier variety of quark. Some theories suggest that strange quark matter might actually be more stable than normal nuclear matter at these densities, which would mean the core of a neutron star could be almost entirely converted to strange matter. If this is true, the neutron star would really be misnamed. It should be called a strange star or a quark star. The name neutron star might describe the outer layers accurately, but completely miss what's happening at the center. Another possibility involves the formation of exotic particles that don't exist in normal matter. At high enough densities, you might get hyperons, which are baryons containing strange quarks, or even condensates of K-mesons or other exotic particles. These possibilities are collectively known as the hyperon puzzle, because their presence should soften the equation of state, the mathematical relationship between pressure and density, which would make it difficult to explain the existence of the heaviest neutron stars we've observed. The most massive confirmed neutron star, PSRJ 0952-0607, has a mass of about 2.35 solar masses. If hyperons formed easily in neutron star cores, the star would collapse into a black hole before reaching such high masses. So either hyperons don't form as easily as we thought, or there's something else in the core that stiffens the equation of state and prevents collapse. What would it actually feel like to approach a neutron star, assuming you had some magical protection against the radiation and gravity? Let's imagine you're in a spacecraft with a magical gravity shield and radiation shield, both of which are absolutely impossible, but let's pretend. As you approach, the first thing you'd notice is the intense radiation. Many neutron stars are pulsars spinning rapidly and beaming radiation from their magnetic poles like cosmic lighthouses. The fastest known pulsar, PSRJ 1748-2446 AD, discovered in 2006 in the globular cluster, Terzan 5 rotates 716 times per second. That's 716 complete rotations every second. At its equator, the surface is moving at about 24% the speed of light. If this pulsar's beam swept across you, you'd be exposed to intense bursts of X-rays and gamma rays 716 times every second each burst, potentially containing more energy than a nuclear explosion. But let's say you're approaching a quieter neutron star one that's not a pulsar. As you get closer, you'd start to notice gravitational effects. Light from stars behind the neutron star would be bent around it, creating multiple distorted images. The neutron star would act like a gravitational lens, warping the appearance of the background sky. Get close enough, and you'd see the entire sky compressed into a narrow ring around the neutron star, with the neutron star itself occupying most of your field of view due to gravitational light bending. You could actually see more than half the neutron star's surface at once because light from the far side would be bent around toward you. If you somehow landed on the surface, time would be running noticeably slower for you compared to someone far from the neutron star, perhaps 15 to 30% slower depending on the star's mass and radius. An hour on the neutron star's surface might be an hour and 15 minutes for distant observers. Your magical gravity shield would need to withstand forces equivalent to having 200 billion Earths stacked on top of every square centimeter of your body. The surface temperature of about 1,000,000 degrees would vaporize any normal matter instantly. And here's something most people don't realize about neutron stars. They have some of the strongest magnetic fields in the universe. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. But there's a special class called magnetaires, which have fields up to 1,000 times stronger, still reaching 10 to the 15th power gas, or about 100 billion teslas. To put that in perspective, a hospital MRI machine produces a field of about 1.5 to 3 teslas. The strongest continuous magnetic field ever created in a laboratory is about 45 teslas. A magnetar's field is about 2 trillion times stronger than that. These magnetic fields are so intense that they do things that seem almost magical. They can create vacuum birefringent splitting light into two polarizations that travel at slightly different speeds, an effect predicted by quantum electrodynamics, but never observed outside of neutron stars. The magnetic field can actually distort the quantum vacuum itself, creating virtual particle-antiparticle pairs that affect how light propagates. If you somehow got within 1,000 kilometers of a magnetar, its magnetic field would be strong enough to disrupt the electromagnetic bonds holding your atoms together. Your molecular structure would be torn apart by magnetic forces. The field could also induce electrical currents in any conductors strong enough to melt them instantly. Can you even imagine what it would be like to exist in a place where the fundamental forces of nature are cranked up to such extreme values that reality itself seems to operate under different rules? Magnetars occasionally undergo starquakes, sudden shifts in their crust that release enormous bursts of energy. On December 27, 2004, a magnetar called SGR-1806-2, located about 50,000 light-years from Earth, produced the largest burst of energy ever recorded from outside our solar system. In just 1/10 of a second, it released more energy than the Sun emits in 150,000 years. The burst of gamma rays and X-rays was so intense that it measurably affected Earth's ionosphere despite the enormous distance. If SGR-1806-2 had been just 10 light-years away, roughly the distance to some of our nearest stars that burst, would have caused a mass extinction on Earth. The interior of a neutron star represents matter in conditions so extreme that we cannot reproduce them in any laboratory. The densest material humans have ever created briefly in particle colliders reaches nuclear density for tiny fractions of a second. A neutron star maintains densities exceeding nuclear density continuously across volumes of cubic kilometers. It's a natural laboratory for studying the strong nuclear force under conditions that can never be replicated on Earth. Every observation we make of neutron stars, every measurement of their masses and radii, every detection of gravitational waves from neutron star mergers tells us something about how matter behaves under these ultimate extremes. In August 2017, gravitational wave detectors picked up the signal of two neutron stars spiraling together and merging an event designated GW170817. This single event confirmed predictions about neutron star collisions, revealed the production site of heavy elements like gold and platinum, and provided direct measurement of the Hubble constant, the expansion rate of the universe. The merger also produced a kilonova, an explosion, powered by the radioactive decay of freshly synthesized heavy elements, and likely created either a very massive neutron star or a black hole. The gravitational wave signal lasting about 100 seconds as the neutron stars spiraled closer and closer before merging gave physicists unprecedented data about the equation of state of ultra-dense matter. So, when we say the interior of a neutron star is unreachable, we mean it in the most absolute sense. It's not just that the conditions would kill you, though they certainly would instantly and completely. It's that the physics operating inside a neutron star is so extreme, so far removed from anything in our experience that the very concepts we use to describe normal matter break down. Atoms don't exist there. Molecules are impossible. The distinction between one particle and another becomes ambiguous in the quantum soup of the core. It's a place where matter itself is redefined, where the rules change, where nature explores configurations that are forbidden everywhere else in the universe, except in the even more extreme environment inside a black hole. And yet, despite their extreme nature, we understand neutron stars remarkably well. We can detect them, study their rotation rates, measure their masses and temperatures, observe their magnetic fields, and even see them collide. They're unreachable, but not unknowable, invisible, but not undetectable, extreme, but not inexplicable. They represent a boundary of matter, the densest configuration that can exist without collapsing entirely into a singularity, the ultimate compression of nuclear matter, before gravity wins completely and creates a black hole. Speaking of places where extreme conditions make existence impossible, we're about to visit somewhere quite different, but no less hostile. Imagine a place not defined by crushing pressure, but by overwhelming heat and radiation. A natural fusion reactor so powerful that it could power our entire civilization for billions of years if we could somehow harness it, yet so dangerous that we cannot approach within millions of miles without vaporizing. We're going inside the sun itself to explore the nuclear furnace at its core, where the temperatures and pressures that forge the very atoms necessary for life make any form of complex matter utterly impossible to survive. Every second deep in the heart of our sun, 600 million tons of hydrogen are being crushed, together with such violence that they fuse into helium, releasing energy equivalent to roughly 100 billion nuclear bombs. This process has been happening continuously for 4.6 billion years, and it will continue for another 5 billion years more. The core of the sun, a sphere roughly the size of Jupiter, buried beneath 432,000 miles of roiling plasma, reaches temperatures of 15 million degrees Celsius and pressures 250 billion times greater than Earth's atmosphere at sea level. It's a place where matter exists only as naked atomic nuclei stripped of their electrons, where photons of light take over 170,000 years to randomly walk their way to the surface, and where the conditions are so extreme that if you could somehow transport a pinhead-sized piece of core material to Earth, it would kill everyone within 100 miles before it cooled down. The sun is so familiar to us that we sometimes forget just how utterly alien it really is. We see it every day rising and setting, providing the light and warmth that makes life on Earth possible. Ancient civilizations worshipped it as a god, which makes sense when you think about it. Without the sun, Earth would be a frozen, lifeless ball of rock, drifting through the cosmic void. Every calorie of energy in your body, every bit of warmth you feel, every gust of wind, every drop of rain, almost all the energy available to life on Earth ultimately comes from the sun. But the mechanism that powers this life-giving star is simultaneously one of nature's most violent processes, and the interior where this mechanism operates is fundamentally unreachable, not just to human explorers, but to any probe or instrument we could ever design. Let's start with a historical puzzle that troubled scientists for most of the 19th century. By the mid-1800s, physicists understood enough about energy and thermodynamics to ask a troubling question: what powers the sun? The sun radiates about 3.8 times 10 to the power of 26 watts of power, meaning it's putting out 380 trillion watts every second. Where does that energy come from? The most obvious answer, that the sun was simply burning like a giant lump of coal, was quickly ruled out. Even if the sun were made of pure coal and pure oxygen, chemical combustion would sustain it for only about 5,000 years at its current luminosity. Geological evidence and evolutionary biology both suggested Earth was far older than that, millions or even billions of years old. which meant the sun must be at least that old too. In 1862, the physicist Lord Kelvin proposed an alternative gravitational contraction. Perhaps the sun was slowly shrinking under its own gravity, and the gravitational potential energy released by this contraction was being converted into heat and light. Kelvin calculated that this mechanism could power the sun for about 20 to 40 million years, which was better than the coal hypothesis, but still far too short. By the early 20th century, radiometric dating of rocks had established that Earth was at least several billion years old, and the sun, being older than Earth, must have been shining for even longer. No conventional energy source could explain it. The answer came from nuclear physics. In 1920, Arthur Eddington, the British astrophysicist, who had helped confirm Einstein's theory of general relativity by observing the bending of starlight during a solar eclipse, proposed that stars might be powered by nuclear fusion, specifically the conversion of hydrogen into helium. At the time, this was an audacious suggestion, because the details of nuclear physics were barely understood. But Eddington did some calculations and realized that if you could somehow fuse 4 hydrogen nuclei into one helium nucleus, the helium would be slightly less massive than the original 4 hydrogens. About 0.7% of the mass would be missing. Where did that mass go? Einstein's famous equation, E equals mc squared, provided the answer. The missing mass was converted into energy. And because c, the speed of light, is such a large number, and because you square it in the equation, even a tiny amount of mass converts into an enormous amount of energy. How much energy? Let's do the math. The sun's mass is about 2 times 10 to the power of 30 kilograms. About 73% of that mass is hydrogen, so roughly 1.46 times 10 to the power of 30 kilograms of hydrogen fuel. If all of that hydrogen could be fused into helium with 0.7% of the mass converted to energy, you'd get about 1.02 times 10 to the power of 28 kilograms of mass converted to energy. Plug that into E equals mc squared, and you get about 9 times 10 to the power of 44 joules of available energy. At the sun's current power output of 3.8 times 10 to the power of 26 watts, that's enough energy to keep the sun shining for about 75 billion years. Of course, the sun can't actually fuse all its hydrogen. Only the core gets hot and dense enough for fusion. In practice, the sun will run out of core hydrogen in about 5 billion years and begin its evolution into a red giant. But the point is that nuclear fusion provides more than enough energy to power the sun for billions of years, solving the mystery that had puzzled 19th century physicists. But understanding what powers the sun and actually observing the interior are 2 very different things. The problem is that the sun isn't transparent. You can't simply point a telescope at it and look inside. The sun is made of plasma-ionized gas, where electrons have been stripped from atoms by the intense heat. And plasma is extraordinarily opaque to electromagnetic radiation. Photons trying to travel through the sun are constantly absorbed and re-emitted by the plasma scattered in random directions, making almost no forward progress. A photon created in the core doesn't simply zip out to the surface in the 8 minutes it would take light to cross that distance. Instead, it takes what's called a random walk, bouncing around randomly through the dense interior for an average of about 170,000 years before finally escaping from the surface. Let me explain that random walk in more detail, because it's one of the most counterintuitive aspects of stellar physics. Imagine you're standing on a city sidewalk trying to walk north to a destination 10 blocks away, but every step you take is in a random direction, north-south, east-west, northeast, with equal probability. Sometimes you'll move toward your destination, sometimes away from it, sometimes parallel to it. On average, after taking n steps, you'll have moved a distance proportional to the square root of n rather than n itself. This means it takes you vastly more steps to reach your goal than if you could simply walk straight there. A photon in the sun's interior experiences something similar. It travels only a tiny fraction of a millimeter before being absorbed by an atom or scattered by an electron. Then it's re-emitted in a random direction, then absorbed again, re-emitted again over and over, billions upon billions of times, gradually working its way outward through sheer random chance. The distance scale is staggering. The core of the sun is about 150,000 kilometers from the surface. Light traveling in a straight line would cover that distance in half a second, but a photon doing a random walk, traveling such tiny distances between scatterings, takes on the order of 100,000 to 200,000 years to escape. During this journey, the photon's energy changes dramatically. Photons created in the core through fusion reactions are high-energy gamma rays. But every time a photon is absorbed and re-emitted, it can be split into multiple lower-energy photons. By the time a photon's energy finally escapes from the sun's surface, it's been degraded and split so many times that the gamma ray has become thousands or millions of visible light or infrared photons. This is why the sun's surface glows with a relatively gentle visible light, rather than sterilizing gamma rays, even though the core is producing gamma rays continuously. This opacity means we cannot see into the sun's interior using any form of electromagnetic radiation from the surface. Everything visible to our telescopes is happening in the photosphere, the thin luminous shell that we think of as the sun's surface, which is only a few hundred kilometers thick. The photosphere is where the plasma finally becomes transparent enough for photons to escape directly into space. Below the photosphere lies 700,000 kilometers of sun that is effectively invisible to conventional observation. So, how do we know what's happening inside? We have three main windows into the solar interior: neutrinos, helioseismology, and theoretical modeling. Let's start with neutrinos. Nuclear fusion in the sun's core doesn't just produce energy and helium. It also produces neutrinos, those ghostly particles that interact so weakly with matter that they can pass through the entire Earth as if it weren't there. Neutrinos created in the sun's core escape immediately within seconds because they don't interact with the plasma. They don't do a random walk. They just fly out in straight lines at nearly the speed of light. By detecting these solar neutrinos on Earth, we can directly sample what's happening in the core right now, in real time. The first solar neutrino detector was built in the 1960s by Raymond Davis Jr. in the Homestake Gold Mine in South Dakota. It consisted of a tank containing 100,000 gallons of perchloroethylene, a cleaning fluid placed deep underground to shield it from cosmic rays. When a neutrino interacted with a chlorine atom in the tank, very rarely it would convert the chlorine into radioactive argon, which Davis could then extract and count. The experiment worked, but there was a problem. Davis detected only about 1/3 as many neutrinos as solar models predicted. This became known as the solar neutrino problem, and it troubled physicists for decades. The solution discovered in the 1990s and early 2000s revealed something fundamental about neutrinos themselves. It turns out that neutrinos can change flavor as they travel, oscillating between electron neutrinos, muon neutrinos, and tau neutrinos. Davis's detector was only sensitive to electron neutrinos, which are what the sun produces. But by the time the neutrinos reached Earth, many had oscillated into other flavors, making them invisible to his detector. When physicists built detectors sensitive to all neutrino flavors, they found the total match predictions, perfectly confirming both our models of solar fusion and revealing a new property of neutrinos. It was a beautiful example of an apparent problem in astronomy, leading to a discovery in fundamental physics. The second window into the solar interior is helioseismology, the study of how the sun vibrates. Just as geologists use seismic waves from earthquakes to map Earth's interior, astronomers use sound waves in the sun to probe its structure. The sun rings like a bell, though, at frequencies far too low for human ears to hear. These oscillations are caused by sound waves traveling through the interior, reflecting off the surface and the core, creating standing wave patterns. By measuring the frequencies of these oscillations very precisely, which we can do by observing tiny Doppler shifts in spectral lines, we can infer the sun's density, temperature, and composition as a function of depth. Helioseismology has confirmed that our theoretical models of the solar interior are remarkably accurate. Now, let's journey through those layers, starting from the core and working outward. The core extends from the center out to about 25% of the sun's radius, roughly 175,000 kilometers. This is where nuclear fusion happens, where the temperature exceeds 13 million degrees Celsius, and the pressure is immense enough to overcome the electrostatic repulsion between positively charged protons and force them to fuse. The specific fusion process happening in the sun is called the proton-proton chain reaction, and it's actually a multi-step process, not a single reaction. In the first step, two protons collide with enough energy to fuse despite their mutual electromagnetic repulsion. One of the protons converts into a neutron via the weak nuclear force emitting a positron and a neutrino, creating a deuterium nucleus. This first step is actually the slowest the bottleneck that controls the sun's power output. The probability of two protons fusing is incredibly low, even at the sun's core temperature. A proton in the core will on average bounce around for about 10 billion years before successfully fusing with another proton. This is why the sun burns so steadily. If fusion were faster, stars would explode. If it were slower, they wouldn't shine. The weak nuclear force which governs this rate-limiting step happens to be calibrated perfectly to make stars stable and long-lived. Once deuterium forms, things proceed more quickly. The deuterium fuses with another proton to create helium-3, releasing a gamma ray. Then two helium-3 nuclei collide and fuse to create helium-4, spitting out two protons in the process. The net result: 4 protons have become one helium nucleus, 2 positrons, 2 neutrinos, and several gamma-ray photons. The positrons immediately annihilate with electrons producing more gamma rays. All told, each complete cycle converts about 0.7% of the original mass into energy as Eddington predicted. The core is also where we find the highest density in the sun, about 150 times the density of water, or roughly 150 grams per cubic centimeter. That's about 15 times denser than lead. And remember, this is plasma, not solid matter. The atoms are completely ionized, stripped into bare nuclei, and free electrons all moving at tremendous speeds dictated by the temperature. The average particle in the core is moving at about 500 kilometers per second, more than 1,000,000 miles per hour. The pressure, about 250 billion atmospheres, is crushing beyond comprehension. To put that in perspective, the deepest point in Earth's oceans experiences a pressure of about 1,000 atmospheres. The sun's core pressure is about 200 million times greater. Above the core lies the radiative zone, extending from about 25% to 70% of the solar radius. In this region, energy transport happens primarily through radiation. Those gamma-ray photons created by fusion in the core are absorbed and re-emitted countless times, gradually working their way outward. The temperature decreases from about 7 million degrees Celsius at the base of the radiative zone to about 2 million degrees at its top. The density also drops from about 20 grams per cubic centimeter to about 0.2 grams per cubic centimeter. Despite the decrease in temperature and density, the radiative zone is still so hot and dense that it would vaporize any material instantly. The plasma here is stable and stratified, with hotter, less dense plasma floating on top of cooler, denser plasma below, and energy slowly diffusing upward through radiation. Then, at about 70% of the way to the surface, something changes. The temperature has dropped enough that hydrogen atoms can hold onto their electrons at least temporarily before being reionized. This increases the opacity of the plasma significantly. Radiation is no longer efficient enough to transport all the energy flowing upward from the core. When a fluid can't transport heat efficiently through conduction or radiation, it starts to convect, and that's exactly what happens. The top 30% of the sun's interior, called the convection zone, is in constant motion. Hot plasma rises, cools as it approaches the surface, releases its heat, and sinks back down, only to be reheated and rise again. It's like water boiling in a pot, except the convection cells are the size of Texas or larger, and the material is moving at speeds of thousands of kilometers per hour. You can actually see the effects of this convection when you look at high-resolution images of the sun's surface. The photosphere is covered with a granular pattern, each granule representing the top of a convection cell. The bright centers are where hot plasma is rising, and the dark edges are where cooler plasma is sinking. Each granule is about 1,000 kilometers across, about the size of Texas or France, and lasts for only about 10 to 20 minutes before dissolving and reforming. There are millions of these granules covering the sun at any given time, creating a constantly shifting, boiling appearance. Larger convection patterns, called supergranules, span about 30,000 kilometers and last for about a day. The convection zone is also where the sun's magnetic field is generated through a process called the dynamo effect. The sun's rotation, combined with the convective motion of electrically conducting plasma, generates powerful magnetic fields that thread through the solar interior and emerge at the surface, creating sunspots, solar flares, and coronal mass ejections. The magnetic field stores enormous amounts of energy and can suddenly release it in explosive events that send billions of tons of plasma hurtling into space at millions of miles per hour. Now, let's talk about why we can never reach the sun's interior or even get particularly close to the sun at all. The fundamental problem is heat and radiation. The sun's surface, the photosphere, has a temperature of about 5,500 degrees Celsius. That's hot enough to vaporize any known material. Tungsten, which has the highest melting point of any element, melts at 3,422 degrees Celsius. Carbon sublimes at around 3,642 degrees Celsius under normal pressure. Hafnium carbide and tantalum carbide, among the most refractory compounds known, break down above 4,000 degrees Celsius. Nothing we could build a spacecraft from could survive contact with the sun's surface, much less the far hotter interior. But you don't have to actually touch the sun to be destroyed by it. The sun radiates energy in all directions, and the intensity of that radiation follows an inverse square law. Get twice as close, and you receive 4 times as much radiation per unit area. The Parker Solar Probe, launched by NASA in 2018, is the closest artificial object ever sent to the sun. At its closest approach, it passes within about 6.9 million kilometers of the sun's surface, well inside the orbit of Mercury. To survive even at that distance, the probe requires a heat shield made of carbon composite foam, sandwiched between carbon fiber layers about 11.5 centimeters thick, designed to withstand temperatures of about 1,377 degrees Celsius. Behind this shield, the spacecraft's instruments remain at a relatively comfortable room temperature. But Parker's solar probe isn't trying to reach the sun's surface. It's studying the corona, the sun's outer atmosphere. It could never get closer without being vaporized. Let's say you wanted to build a probe that could descend into the sun, not just orbit near it. What would you need? First, you'd need materials that could survive temperatures of millions of degrees. We don't have such materials. We can't even imagine what such materials would be. At those temperatures, molecular bonds don't exist. Chemical structures break down entirely. Atoms themselves are ionized into bare nuclei and free electrons. There's no solid or liquid state, only plasma. Any probe would be torn apart at the atomic level long before reaching the core. Second, you'd need to deal with the pressure. The pressure at the core is 250 billion times Earth's atmospheric pressure. The deepest we've ever sent a probe on Earth is to the Mariana Trench, about 11 kilometers deep, where the pressure is about 1,100 atmospheres. We can build vessels to withstand that, but 250 billion atmospheres. The probe would be crushed into neutron star density, except it would be vaporized by the heat long before the pressure became the limiting factor. Third, there's the radiation. The sun's core is producing about 276.5 watts per cubic meter through fusion. That doesn't sound like much about the same power density as a compost heap, but that's a continuous output happening in every cubic meter, adding up to the sun's total luminosity. More importantly, the radiation in the core isn't visible light. It's high-energy gamma rays, each photon carrying enough energy to tear molecules apart and damage atomic nuclei. The radiation environment is so intense that any complex structure would be disintegrated almost instantly. Have you ever wondered what would happen if you could somehow teleport a cube of sun core material to Earth? Let's say a cubic centimeter about the size of a sugar cube. It would contain about 150 grams of plasma at 15 million degrees Celsius. The thermal energy alone would be approximately 150 grams times 1,000 joules per gram per degree times 15 million degrees, which comes out to about 2.25 times 10 to the power of 12 joules, or about half a megaton of TNT equivalent. That's comparable to a large thermonuclear weapon. And it would release that energy in a fraction of a second as it explosively expanded and cooled. A cubic centimeter of sun core could devastate a city. But here's an interesting thought experiment. What if we approach the problem differently? What if instead of sending a probe into the sun, we try to drill a tunnel? After all, we drill into the Earth to study its interior. Could we drill into the sun? The answer is no, for multiple reasons. First, the sun isn't solid. It's entirely gaseous, or more precisely, plasma. There's nothing to drill through. Any tunnel you created would immediately close behind you as plasma flowed back in. Second, the conditions are so extreme that your drilling equipment would vaporize instantly. Third, and perhaps most fundamentally, the sun's interior is in hydrostatic equilibrium, with pressure increasing with depth according to the weight of material above. Any void you created would be filled immediately by plasma flowing in at tremendous speed and pressure. The closest we've come to visiting the sun's interior is through neutrino detection, as I mentioned earlier. Neutrinos produced in the fusion reactions at the core escape almost instantly and can be detected on Earth, giving us real-time information about what's happening in the core. But this isn't really visiting. It's more like receiving messages from an unreachable place, postcards from the sun's heart, telling us it's still burning, still fusing hydrogen into helium, still powering the light that makes life on Earth possible. The sun will continue to shine for about another 5 billion years, gradually brightening as helium accumulates in the core and the fusion rate slowly increases. Eventually, the core will run out of hydrogen fuel. At that point, the core will contract and heat up, while the outer layers will expand dramatically, transforming the sun into a red giant. The core will eventually become hot enough to fuse helium into carbon and oxygen, and the sun will remain in this phase for a few 100 million years before finally expelling its outer layers and leaving behind a white dwarf, a dense ember slowly cooling over trillions of years. But throughout its entire main sequence lifetime, the sun's interior will remain unreachable, a nuclear furnace operating at temperatures and pressures we can model mathematically, but never experience directly. It's a place where the fundamental processes that power nearly all the stars in the universe, that forge the light elements into heavier ones, that release the energy-enabling complex chemistry, and ultimately life happen, continuously hidden from view, accessible only through the subtle messages carried by neutrinos and the patient analysis of surface oscillations. From this realm of overwhelming heat and radiation, we're about to journey to a very different kind of unreachable place. Not a place of extreme density or temperature, but a place defined by absence rather than presence, by emptiness rather than fullness. We're going to explore the Boötes void, a region of space so vast and so empty that if our galaxy were somehow transported there, our night sky would be almost completely dark, with only a handful of distant faint galaxies visible where we now see thousands. It's a cosmic desert, an ocean of nothingness spanning hundreds of millions of light years, and understanding why such voids exist tells us something profound about the structure of the universe itself. Imagine waking up one morning, looking out your window, and discovering that every house, every building, every person for hundreds of miles in all directions has vanished, leaving you alone in an empty landscape stretching to the horizon. Now multiply that emptiness by billions, and extend it not across miles, but across hundreds of millions of light years, and you'll begin to grasp the scale of cosmic voids. The Boötes void, discovered in 1981, is a spherical region of space roughly 330 million light years in diameter that contains almost nothing. Where you'd expect to find 10,000 galaxies based on the average density of the universe, there are only about 60. It's not empty in the absolute sense, but it's so profoundly underpopulated that astronomers initially called it the Great Nothing. And if an intelligent civilization somehow found itself in the center of this void, they would look up at their night sky and see almost total darkness, with perhaps a dozen faint smudges of light, where we see thousands of galaxies. The discovery of the Boötes void was accidental and slightly unsettling. In 1981, astronomer Robert Kirshner and his colleagues at the University of Michigan were conducting a survey of galaxy redshifts in the direction of the constellation Boötes the Herdsman. They were measuring how fast galaxies were receding from us due to cosmic expansion, mapping out the three-dimensional structure of the universe in that region of space. What they found shocked them. As they plotted galaxy positions in 3 dimensions, accounting for distance based on redshift, a huge empty region appeared in their data. At first, they thought it must be an error, perhaps an instrumental problem, or a miscalculation. Empty regions of this scale weren't part of the standard cosmological models of the time, but as they gathered more data and confirmed their measurements, the reality became clear. There really was a vast region of space centered roughly 700 million light-years away from Earth that contained almost no galaxies. The Boötes void spans about 330 million light-years across, though its exact boundaries are somewhat fuzzy, since voids don't have sharp edges, but rather gradually blend into the surrounding cosmic structure. To put that size in perspective, our entire local group of galaxies, including the Milky Way Andromeda and dozens of smaller galaxies, occupies a region only about 10 million light-years across. The Boötes void could contain more than 30,000 structures the size of our local group, arranged in a 3-dimensional grid. And yet, it's nearly empty, containing only about 60 known galaxies, most of them very small and dim. The density of galaxies in the void is roughly 10% of the average density in the surrounding universe, meaning it's about 90% emptier than normal space, which is already pretty empty to begin with. Now, when we say the void is empty, we need to be precise about what that means. It's not a perfect vacuum. It's not devoid of all matter. There's still dark matter distributed throughout the void, and there's still the intergalactic medium-thin wisps of gas at extremely low densities. What's missing is the galaxies, the luminous matter, organized into stars and stellar systems that we can see with our telescopes. The void is severely underdense in galaxies, and that's what makes it so striking and so strange. To understand why voids exist and why they're unreachable in any meaningful sense, we need to understand the large-scale structure of the universe. When cosmologists map the distribution of galaxies across billions of light-years, they don't find a uniform, homogeneous distribution. Instead, they find that galaxies are organized into an intricate 3-dimensional pattern that astronomers often describe as a cosmic web. Galaxies cluster together into groups and clusters, which are connected by long filaments of galaxies stretching across hundreds of millions of light years. These filaments surround and define vast empty regions, the voids. If you could somehow view the large-scale structure of the universe from outside, it would look like a vast three-dimensional foam or sponge with galaxies concentrated in thin sheets and filaments surrounding bubble-like voids. This structure has its origins in the very early universe in the tiny quantum fluctuations that existed in the first fraction of a second after the Big Bang. These fluctuations, regions of slightly higher or lower density than average, were stretched to cosmic scales by inflation, the brief period of exponential expansion that occurred when the universe was only about 10 to the power of minus 36 seconds old. After inflation ended, these density fluctuations became the seeds for all the structure we see today. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter, making them even denser, which increased their gravity further in a runaway process that amplified small differences into large structures over billions of years. But here's the key insight: while overdense regions were getting more overdense pulling matter toward them through gravity, underdense regions were getting even more underdense. Matter was flowing out of these regions toward the overdense areas, evacuating the voids and building up the filaments and clusters. Over billions of years, this process created the cosmic web structure we observe today, with galaxies concentrated in the densest regions and vast voids representing the regions that matter drained away from. The Boötes void is one of the largest and most prominent voids discovered, but it's not unique. Surveys have found hundreds of voids throughout the observable universe. There's the Sculptor void, the Eridanus, supervoid, the Giant void, Canes Venatici, and many others. Voids appear to be a fundamental feature of cosmic structure, occupying perhaps 40 to 60% of the total volume of the universe, though they contain only a tiny fraction of the galaxies. In fact, despite occupying most of the volume, voids contain less than 10% of the luminous matter in the universe. Most galaxies live in the filaments and clusters, the dense regions of the cosmic web. Voids are the spaces between. Now, let's do a thought experiment. Imagine you're an astronomer living on a planet orbiting a star in one of the 60 galaxies inside the Boötes void. And let's say your galaxy is near the center of the void, about 150 million light-years from the nearest wall where galaxies become more common. What would your night sky look like? On Earth, when we look up on a clear, dark night, far from city lights, we can see thousands of stars with the naked eye, and we see the Milky Way stretching across the sky, a luminous band of countless stars, too distant to resolve individually. Through telescopes, we can see nearby galaxies like Andromeda, visible as a faint smudge of light, 2.5 million light-years away. Deep telescope observations reveal thousands of galaxies in every direction, some billions of light-years distant. But from the center of the Boötes void, your night sky would tell a very different story. You'd still see stars, of course the stars in your own galaxy would be just as visible as stars in the Milky Way are to us. But when you look beyond your galaxy, you'd see almost nothing. The nearest neighboring galaxies would be tens of millions of light-years away, appearing as extremely faint, tiny smudges of light, far dimmer than Andromeda appears from Earth. Where we can see thousands of galaxies with powerful telescopes, you might see only a few dozen, all of them faint and distant, scattered across the sky like isolated islands in an infinite ocean. The cosmic web structure, so apparent in our surveys, would be invisible to you because you'd be inside one of the bubbles surrounded by the empty interior of the void. This has profound implications for how a civilization in such a location would understand the universe. Throughout human history, our view of the cosmos has been shaped by what we can observe. Ancient humans seeing thousands of stars imagined them as part of a celestial sphere or as distant suns. When telescopes revealed that some fuzzy patches were actually distant galaxies, we realized the universe was far larger than we'd thought. Observations of galaxy clusters and large-scale structure led us to understand dark matter and cosmic evolution. But a civilization in the Bode's void would have far fewer observational clues. They'd see their own galaxy, of course, and they'd probably discover other galaxies eventually with powerful enough telescopes. But the sparsity of their cosmic neighborhood might lead them to radically different conclusions about the nature and structure of the universe. They might, for instance, conclude that galaxies are rare, isolated objects scattered sparsely through an enormous, mostly empty cosmos. They might have difficulty discovering the cosmic web structure because they'd need extraordinarily deep surveys to see it. They might take much longer to discover the expansion of the universe because measuring redshifts and distances to construct a Hubble diagram requires having enough galaxies to observe, and galaxies are scarce in voids. Their cosmology might develop along very different lines than ours, not because they were less intelligent or less scientifically minded, but simply because their observational vantage point was different. Can you imagine how isolated such a civilization might feel once they realized how empty their cosmic neighborhood was? But here's what makes the Boötes void truly unreachable. It's not just the emptiness itself, though. That's striking enough. It's the scale combined with the expansion of space. The void is 330 million light-years across, centered about 700 million light-years from Earth. Even if we could travel at the speed of light, which we can't, it would take 700 million years to reach the void and another 165 million years to reach its center. And during that journey, the expansion of space would be carrying the void away from us. At those distances, the expansion contributes a recession velocity of about 16,000 kilometers per second, roughly 5% the speed of light. The void isn't beyond our cosmic horizon, so it's not unreachable in the same sense as regions beyond the Hubble sphere, but it's so far away and so empty that any exploration would be meaningless. What would you even be traveling to? There's nothing there to see, nothing to study, that you couldn't study from a distance, no reason to make the journey except to say, you'd been to one of the emptiest regions of space. It's unreachable, not because physics forbids the journey, but because the journey would be pointless, a billion-year voyage to arrive at nothing. You'd pass through billions of cubic light-years of space containing only a handful of dim dwarf galaxies. And after that incomprehensibly long journey, you'd find yourself in the emptiest, loneliest region of the observable universe, with almost nothing to observe except the distant walls of the void, hundreds of millions of light-years away in every direction. There's also a deeper sense in which voids are unreachable. As the universe continues to expand and the acceleration driven by dark energy continues to increase, the large-scale structure will gradually dissolve. Galaxies that are currently part of the cosmic web, but not gravitationally bound to each other, will drift apart, carried by the expansion of space. In the extremely distant future, tens or hundreds of billions of years from now, nearly all galaxies will have crossed beyond each other's cosmic horizons, becoming forever inaccessible, as we discussed earlier. The universe will become, in effect, one vast void with tiny pockets of matter, the gravitationally bound galaxy clusters, separated by distances so immense that they can never communicate or interact. The Boötes void, then, is a preview of the universe's far future, a glimpse of the cosmic loneliness that awaits all structures not bound together by gravity strong enough to resist the expansion. There's something deeply melancholic about voids, something that appeals to our sense of cosmic perspective. We live in a galaxy, part of a group, near a supercluster, embedded in a filament of the cosmic web. We're in one of the universe's crowded neighborhoods, relatively speaking. From our vantage point, the sky is rich with galaxies and the universe appears full of structure and complexity. But step back and look at the big picture, and you realize that we're actually living in a thin shell of matter surrounding vast volumes of near emptiness. Most of the universe's volume is void. We're not in the typical place. We're in one of the rare overdense regions where galaxies cluster together. Most of space is far emptier than our cosmic backyard. This realization comes from galaxy surveys conducted over several decades, starting in the 1980s and continuing through today. The CFA Redshift Survey, conducted by the Harvard-Smithsonian Center for Astrophysics, was one of the first to reveal the cosmic web structure in the 1980s. Later, surveys like the 2-degree Field Galaxy Redshift Survey and the Sloan Digital Sky Survey mapped millions of galaxies in 3 dimensions, revealing the cosmic web in exquisite detail and discovering numerous voids. The Sloan Digital Sky Survey in particular, which began observations in 2000, has created the most detailed 3-dimensional map of the universe ever made, covering over a third of the sky and measuring precise redshifts for millions of galaxies. These surveys confirmed that voids are a ubiquitous feature of large-scale structure. They also revealed that voids have structure. They're not perfectly spherical or perfectly empty. Some voids are elongated, others are more spherical. Some contain a few dwarf galaxies, others are almost entirely devoid of luminous matter. The boundaries of voids, called void walls, are regions of higher galaxy density, where multiple voids meet, creating sheet-like concentrations of galaxies. Some of the largest known structures in the universe, like the Sloan Great Wall, a vast concentration of galaxies stretching over 1.3 billion light-years, are actually the boundaries where multiple voids come together. Studying voids tells us a great deal about cosmology and the nature of dark energy. The formation and evolution of voids are sensitive to the properties of dark matter and dark energy, the 2 mysterious components that make up 95% of the universe's total energy density. By measuring the size distribution of voids, how many large voids versus small voids exist, cosmologists can test theories about how dark energy behaves. Some models predict that dark energy's strength might vary over time or space, and void statistics can help distinguish between different models. Voids are like cosmic laboratories, natural experiments that test our understanding of gravity, dark matter, and dark energy on the largest scales. There's also been speculation, though it's very much a minority view, about whether we might live in a large void. The idea is that if the Milky Way were located in an underdense region, perhaps not as extreme as the Barytes void, but still significantly below average density, this could affect our observations of distant supernovae and potentially explain some cosmological anomalies. However, detailed surveys of our local universe show that we're not in a significant void. We're part of the Virgo supercluster, a large concentration of galaxy clusters, which is itself part of an even larger structure called the Laniakea supercluster. Our cosmic neighborhood is, if anything, denser than average, not less dense. The question of what's actually inside voids in the space between the few galaxies that inhabit them is interesting. There's certainly dark matter distributed in a web-like pattern, even in the voids, though, at much lower density than in filaments and clusters. There's also the intergalactic medium, ionized hydrogen and helium. At extremely low densities, perhaps 1 atom per cubic meter, heated to temperatures of millions of degrees by the ultraviolet radiation from galaxies and quasars. This hot ionized gas fills the space between galaxies throughout the universe, including in voids, though it's denser in filaments and thinner in voids. Some voids contain tenuous filaments of gas connecting the few galaxies inside them, visible only through very sensitive observations. In 2019, astronomers using the Hubble Space Telescope reported detecting some of this intergalactic medium inside voids by observing how it absorbed light from distant quasars passing through the void. The gas was there just extremely diffuse, perhaps 100 times less dense than the intergalactic medium in normal regions of space. This makes sense. The gas, like the galaxies, has drained toward the overdense regions over billions of years, leaving the voids depleted but not perfectly empty. There's also been speculation about whether voids might harbor dark matter substructures, small clumps of dark matter, that never accumulated enough baryonic matter to form visible galaxies. If dark matter has complex properties beyond what the simplest models assume, there might be small-scale structure in voids that we can't see directly because it doesn't contain stars or gas. Detecting such structures would require gravitational lensing observations or future direct dark matter detection experiments, and it remains an open question in cosmology. The existence of voids also raises philosophical questions about the nature of space and emptiness. What does it mean for a region to be empty? In everyday language, an empty room is a room containing no objects. But in physics, even the emptiest room contains air electromagnetic radiation, cosmic rays, neutrinos passing through quantum vacuum fluctuations, and gravitational fields. True emptiness in the absolute sense doesn't exist. Even the vacuum of space, even the interior of a cosmic void, is filled with quantum fields, dark matter, the intergalactic medium, and the fabric of space-time itself, permeated by dark energy. The Boeta's void then isn't empty in any absolute sense. It's just remarkably underpopulated by galaxies compared to what we'd expect. It's a place where the normal density of cosmic structure is reduced by 90%, creating a region that would appear almost featureless and dark to observers within it. And that's what makes it unreachable in the most profound sense. It's not that we can't travel there, though the distances are prohibitive. It's that there's no reason to go, nothing to find, no destination worth the incomprehensible journey. It's the loneliest place in the universe, not because of what threatens you there, but because of what isn't there, the absence of the richness and complexity and density of structure that makes other regions of the universe interesting. From this meditation on cosmic emptiness and the structure of the universe at its largest scales, we're about to explore something entirely different, a place that might not exist at all, except in the equations of general relativity. While black holes are real objects we've observed and studied, Einstein's equations also predict the existence of their time-reversed counterparts, objects that would emit matter and energy rather than absorbing them, places that would be impossible to enter rather than impossible to escape. These hypothetical objects are called white holes, and they represent perhaps the most theoretical and speculative of all our unreachable destinations, places that mathematics permits, but that the universe seems to have decided against creating. Imagine a place that does the exact opposite of a black hole. Instead of trapping everything that falls in it, explosively spews matter and energy outward, refusing to let anything enter. A place where time flows backward from our perspective, where causality operates in reverse, where the mathematics says it should exist, but the universe appears to have vetoed the possibility. This is a white hole, the time-reversed twin of a black hole, an object so strange that most physicists suspect they don't actually exist anywhere in our universe. And if they don't exist, then white holes represent the most peculiar category of unreachable place. We've discussed a location that's unreachable, not because it's too far away or too hostile, but because it might not be real at all, existing only in the abstract realm of mathematical solutions that nature has chosen not to implement. White holes emerge from the same equations that predict black holes' Einstein's field equations of general relativity. When physicist Carl Schwarzschild found the first exact solution to Einstein's equations in 1916, describing the curvature of space-time around a spherically symmetric mass, his solution actually contained two regions, not one. There was the black hole region, where space-time curves so severely that escape becomes impossible. But there was also a mathematically symmetric region, with opposite properties, a white hole, where the extreme curvature prevents anything from entering. Schwarzschild's solution is time-symmetric, meaning if you reverse the direction of time in the equations, you get an equally valid solution. Run a black hole backward in time, and you get a white hole. To understand white holes, let's first recall what we learned about black holes. A black hole has an event horizon, a boundary where the escape velocity equals the speed of light. Anything crossing the event horizon from outside to inside becomes trapped, unable to escape, because that would require traveling faster than light, which physics forbids. Time and space trade roles inside the event horizon, so that moving toward the singularity becomes as inevitable as moving forward in time. The event horizon is a one-way membrane permeable only from outside to inside, like a trap door that swings only one direction. A white hole would have the exact opposite structure. It would have a horizon often called a white hole horizon, where anything trying to approach from outside would need to travel faster than light to cross. In other words, you can't enter a white hole any more than you can catch up to a beam of light. The white hole horizon would also be a one-way membrane, but permeable only from inside to outside. Matter and energy would emerge from the white hole, fountaining outward across the horizon, but nothing could fall in. It's as if the white hole is a region of space-time that has a past but no future, at least not a future that connects to the rest of the universe. Anything inside the white hole, any matter or energy that exists there, is destined to eventually cross the horizon and emerge into the external universe. The mathematics that describes this is perfectly valid. Einstein's equations don't distinguish between past and future, between causes and effects. They're time-symmetric, meaning if you have a solution where a matter collapses to form a black hole, you automatically have a solution where matter explodes outward from a white hole. The laws of physics at their most fundamental level don't have a built-in arrow of time. That arrow emerges from thermodynamics, from the increase of entropy. But general relativity itself doesn't care which direction time flows. So, if the math works, why do most physicists think white holes don't exist? The answer comes down to stability causality and the second law of thermodynamics. Let's start with stability. In the 1960s and 1970s, physicists began studying what would happen if you perturbed a white hole slightly, if you imagined it interacting with its environment rather than existing in perfect isolation. What they found was deeply problematic. White holes appear to be fundamentally unstable. Any small perturbation, any matter or radiation falling toward the white hole from the outside universe, would cause the white hole horizon to become singular, to develop infinite curvature, essentially destroying the white hole structure. Unlike black holes, which happily absorb anything that comes near them and grow larger in the process, white holes seem unable to coexist with a universe that contains anything other than themselves. Think about it this way. The universe is filled with matter and radiation. There are photons from the cosmic microwave background streaming through every point in space. There are neutrinos from distant stars. There are gravitational waves rippling through space-time. There's the quantum vacuum with its fluctuations. A white hole sitting in this environment would be constantly bombarded by all this stuff trying to fall in. But, by definition, a white hole can't let anything fall in. The horizon prevents it. So, what happens when a photon from the cosmic microwave background encounters a white hole horizon? The mathematical analysis suggests the horizon would become unstable, the smooth space-time structure would break down, and the white hole would cease to exist as a well-defined object. It's as if white holes are too fragile to survive in a real universe. There's also a profound issue with causality and the arrow of time. White holes would represent a violation of the second law of thermodynamics in a certain sense. The second law says that entropy disorder always increases in isolated systems. A black hole swallowing matter increases the entropy of the universe because black holes have enormous entropy associated with their event horizons proportional to the area of the horizon. But a white hole would be doing the opposite, ejecting organized matter and energy into the universe, seemingly creating order from disorder. While this doesn't technically violate the second law, it requires initial conditions that seem extraordinarily unlikely, a perfectly organized state existing in the white hole's past, that then decays by ejecting matter. In practice, we never see such processes in nature. Time's arrow points from order to disorder, from low entropy to high entropy, and white holes seem to point the wrong way. Let's imagine what would happen if a white hole actually existed. Picture a white hole sitting in space with its horizon marking the boundary. From outside approaching the white hole, you'd see matter and radiation streaming outward from the horizon at high velocities, perhaps approaching the speed of light. As this material crossed the horizon and entered the external universe, it would appear suddenly as if materializing out of nothing. You couldn't see what was happening inside the white hole because just as light can't escape from a black hole, light can't enter a white hole to illuminate its interior for external observers. If you tried to approach the white hole, you'd find it impossible to get close. The material streaming outward would push you back. But even ignoring that, the structure of space-time itself prevents approach. As you accelerated toward the white hole horizon trying to reach it, you'd find that the horizon remained unreachable, receding from you, no matter how fast you traveled. The white hole horizon is a light-like surface, meaning only something traveling at the speed of light could reach it from outside, and nothing with mass can travel at the speed of light. It's exactly the opposite of a black hole where you can fall in but can't escape. With a white hole, you can escape easily. You just move away, but you can't enter no matter how hard you try. From the inside, if you somehow existed within a white hole, your experience would be strange. You'd see the horizon as a boundary in your past, not your future. Everything in the white hole interior would be moving inexorably toward the horizon, destined to cross it and emerge into the external universe. You couldn't avoid this fate any more than you can avoid aging forward in time. Inside a white hole, the direction toward the horizon would be time-like rather than space-like, meaning moving away from the horizon would be like trying to travel backward in time, impossible. The interior of a white hole would be a region of space-time that has a definite beginning, the singularity or the deep past, but that empties itself out over time, ejecting everything across the horizon until nothing remains. But here's where things get even more speculative and interesting. Some physicists have wondered whether black holes and white holes might be connected, forming wormholes, tunnels through space-time that connect distant regions. The complete mathematical solution that Schwarzschild found actually includes both a black hole and a white hole connected by a wormhole called the Einstein-Rosen bridge. In this solution, anything falling into the black hole would travel through the wormhole and emerge from the white hole in another region of space-time. It's a beautiful idea, but there are severe problems with it. First, the Einstein-Rosen bridge in Schwarzschild's solution is not traversable. The wormhole forms and then pinches off so quickly that nothing, not even light, has time to pass through it before it collapses. The geometry of space-time closes the tunnel before you can use it. Second, even if you could somehow hold the wormhole open, which would require exotic matter with negative energy density, something we've never seen and that probably doesn't exist, the connection would be one way. You could enter the black hole and travel through the wormhole, but you'd emerge from the white hole into a different space-time, not back into our universe. The white hole would be spewing you out into some disconnected region of reality, and you could never return or send information back. It's not a useful shortcut through space. It's an exit to somewhere else, entirely assuming such connections even make sense physically. Could white holes have formed in the early universe? This is one of the few scenarios where physicists take the idea semi-seriously. In the extreme conditions of the Big Bang, where space-time was extraordinarily curved and matter and energy densities were enormous, it's conceivable that some regions might have had the right initial conditions to form white hole-like structures. Some cosmologists have speculated that the Big Bang itself might be understood as a kind of white hole, a singular event from which all matter and energy in our universe emerged. In this view, the entire observable universe started as something like a white hole that exploded outward 13.8 billion years ago, and we're living in the aftermath of that explosion. This is an intriguing idea, but it faces significant challenges. The Big Bang, as we understand it from standard cosmology, was a hot, dense state that expanded everywhere simultaneously. It didn't have a localized horizon like a white hole would. The Big Bang happened at every point in space at the same time, or more accurately, it represents the earliest moment of time itself, before which the concept of before doesn't make sense. A white hole, by contrast, would be a localized object with a definite boundary separating its interior from the external universe. The two concepts don't map onto each other cleanly, though there are some interesting parallels in the mathematics. Another possibility, though highly speculative, is that white holes might form as the end state of black holes. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon, and over vast stretches of time, this Hawking radiation causes black holes to evaporate, losing mass until they eventually disappear. But what happens at the very end of this process? As a black hole shrinks down to near zero mass, approaching the Planck scale, where quantum gravity effects become important, our theories break down. We don't have a complete theory of quantum gravity to describe the final moments of black hole evaporation. Some physicists have speculated that the endpoint might be a white hole, that the collapsing matter that formed the black hole billions of years ago might finally emerge quantum mechanically tunneling through space-time to appear as a white hole ejecting the matter back out. This idea, proposed by physicists Carlo Rovelli and Hal Haggard, among others, suggests that black holes might be long-lived transient objects that eventually convert to white holes through quantum effects. From outside, you'd see matter fall into a black hole, but that matter wouldn't truly be destroyed. Instead, it would be delayed, trapped in the black hole for an extremely long time, perhaps billions or trillions of years, before quantum mechanics allowed it to escape through a white hole transition. The mathematics of this process involves loop quantum gravity, one of the candidate theories for quantum gravity, and it remains highly controversial and uncertain. Have we ever observed anything that might be a white hole? The answer is no, not definitively. In the 1970s, there was brief excitement when astronomers discovered gamma-ray bursts, sudden intense flashes of gamma radiation coming from random directions in space. For a while before their true nature was understood, some scientists wondered if these might be white holes ejecting matter. But we now know that gamma-ray bursts are caused by supernova explosions of massive stars, or by collisions of neutron stars, not by white holes. Every candidate white hole observation has turned out to be something else when examined more carefully. There have been more recent claims about possible white hole detections, usually involving unusual transient astronomical events that are hard to explain with conventional models. For instance, some fast radio bursts, mysterious pulses of radio waves, lasting only milliseconds, have properties that are difficult to explain, and a few physicists have speculatively suggested white holes as a possible source. But the overwhelming consensus is that these phenomena have conventional explanations involving neutron stars, black holes, or other known astrophysical objects. There's no compelling evidence that white holes exist in our universe. Can you imagine being a physicist trying to determine whether an object predicted by your best theory actually exists in reality? There's also a concept called the cosmic censorship hypothesis proposed by Roger Penrose in 1969, which might explain why we don't see white holes. The hypothesis states that the universe doesn't allow naked singularities, singularities not hidden behind event horizons, to exist. A white hole would violate this principle in a sense. While the white hole horizon does hide the singularity from outside observers, the white hole is essentially ejecting matter from a singularity into the universe, which seems contrary to the spirit of cosmic censorship. Penrose's hypothesis suggests that nature has mechanisms to prevent such situations from arising, that the laws of physics conspire to ensure that singularities remain safely hidden behind black hole horizons rather than exposed as white holes. This brings us to a deeper question about the relationship between mathematics and reality. Physics is written in the language of mathematics, and when we solve equations, we often find multiple solutions. But not every mathematical solution corresponds to physical reality. The equations of motion for a thrown ball have solutions where the ball goes up and solutions where the ball goes down, but we only see balls going up initially, because that's the solution corresponding to the initial conditions we created by throwing the ball upward. Similarly, Einstein's equations have both black hole and white hole solutions. But our universe seems to produce only black holes, presumably because the initial conditions and evolutionary dynamics favor black hole formation, while making white holes impossible or extraordinarily unlikely. This is a subtle but important point about how science works. Mathematics tells us what's possible, what's allowed by the laws of physics. But it doesn't tell us what actually exists. That requires observation experiment and an understanding of how systems evolve over time, given realistic initial conditions and environments. White holes are mathematically possible, but physically implausible. They're like a chess move that's legal according to the rules, but that no experienced player would ever make because it leads immediately to a losing position. The unreachability of white holes then is fundamentally different from the unreachability of black hole interiors or cosmic horizons or neutron star cores. Those places are unreachable because physics makes them inaccessible or hostile to exploration. White holes are unreachable because they probably don't exist, because the universe has apparently decided not to create them despite their mathematical legitimacy. It's a strange form of unreachability, the unreachability of the hypothetical, the theoretical, the purely mathematical. Yet there's value in studying white holes, even if they don't exist. They help us understand the structure of space-time, the properties of horizons, the nature of time reversal symmetry in physics. They push us to think about causality entropy and the arrow of time. They reveal the difference between what's mathematically possible and what's physically real, a distinction that's crucial for understanding how theoretical physics relates to the observable universe. And they remind us that our theories, powerful as they are, sometimes predict things that nature chooses not to implement for reasons we're still working to fully understand. The study of white holes also connects to broader questions about the initial conditions of the universe. Why did the universe start in a low entropy state, a highly organized condition that has been decaying toward disorder ever since? Why does time have an arrow? Why do we remember the past, but not the future? These deep questions in cosmology and thermodynamics are related to the question of why white holes don't seem to exist. The universe's initial state was special in ways that favor black hole formation over white hole formation, that favor increasing entropy over decreasing entropy, that give time its direction. Understanding why nature made these choices would be a profound advance in physics. So, white holes remain theoretical constructs, mathematical shadows cast by Einstein's equations, places that could exist in principle but probably don't exist in practice. They're unreachable not because we can't build a spacecraft to reach them, not because extreme conditions would destroy us, not because they're beyond a cosmic horizon, but because the destination itself is likely fictional, a mathematical mirage with no physical substance. Among all the unreachable places we've explored tonight, white holes are unique in this respect. They represent the limits not of exploration, but of existence itself, the boundary between what mathematics permits and what reality allows. As we near the end of our journey through the universe's most unreachable places, it's time to step back and reflect on what all these boundaries, these limits, these impossible destinations tell us about the nature of reality and our place within it. We've traveled from black hole horizons to cosmic voids, from quantum foam to nuclear furnaces, from expanding space to hypothetical objects that likely don't exist. And through all these explorations, a pattern has emerged, a recognition that the universe has drawn lines defining what's possible, and that understanding these boundaries is itself a profound form of knowledge. Let's gather these insights together and discover what the unreachable teaches us about the reachable, what the unknowable reveals about what we can know, and what it means to be conscious beings aware of our own limitations. We've traveled far tonight, you and I, further than any spacecraft could take us, deeper than any probe could venture. We've stood at the edge of black hole event horizons and watched space-time itself tear causality apart. We've witnessed galaxies racing away from us, faster than light, can chase them slipping forever beyond the cosmic horizon into regions we can never observe. We've shrunk down to the Planck scale where reality dissolves into quantum foam. And we've journeyed to the centers of neutron stars, where matter is crushed into configurations so exotic that physicists name them after pasta. We've felt the nuclear fire at the sun's core, visited the profound emptiness of the Boeta's void, and contemplated the mathematical ghosts of white holes that probably don't exist anywhere in our universe. 7 places, 7 different categories of impossibility, 7 boundaries that the universe has drawn around what we can reach, what we can know, what we can experience. And now, as our journey draws to a close, it's worth asking, what have we learned? What do these unreachable places tell us about the universe and about ourselves? Because these boundaries aren't just obstacles or limitations, they're revelations. They're telling us something profound about the structure of reality, about the laws that govern existence, about what it means to be conscious beings trying to understand a cosmos vastly larger and stranger than ourselves. Let's start with a humbling observation. We've discovered tonight that 99.9999% of the universe, perhaps much more than that, is fundamentally beyond our reach. The 94% of galaxies already beyond our cosmic horizon, the interiors of black holes hidden behind event horizons, the quantum foam at the Planck scale where our theories break down, the cores of neutron stars where matter exists in states we can barely comprehend, the nuclear furnace of the sun burning with energies that would vaporize any probe we could send, the vast cosmic void separated from us by distances measured in hundreds of millions of light years. Even white holes, if they existed, would be unreachable by definition. When you add it all up, when you calculate the fraction of space-time that humans could theoretically visit or directly observe, the number is so fantastically small that it approaches 0. This should make us pause. We live in an era of unprecedented exploration. We've sent spacecraft to every planet in our solar system. We've landed rovers on Mars and driven them across ancient lake beds. We've flown a probe past Pluto, revealing a world far more complex and beautiful than anyone expected. We've detected gravitational waves from colliding black holes a billion light-years away. We've photographed the shadow of a supermassive black hole in the center of a distant galaxy. We've mapped the cosmic microwave background with exquisite precision, seeing the universe as it was just 380,000 years after the Big Bang. Our reach has extended so far, our knowledge has grown so vast, that it's easy to imagine we're on the verge of understanding everything, of answering every question, of exploring every mystery. But the places we visited tonight remind us that this is an illusion. For all our achievements, and they are genuinely remarkable, we're still confined to a tiny bubble of the cosmos, a vanishingly small region of space and time, where conditions happen to permit our existence and our observations. Beyond this bubble lie realms that are not just unexplored, but unexplorable, not just unknown, but unknowable, not just far away, but fundamentally inaccessible. The universe is under no obligation to be fully knowable to us. It's under no obligation to permit us access to all its secrets. And the boundaries we've encountered tonight are the universe's way of saying gently but firmly, there are things you cannot reach, places you cannot go, questions you cannot answer through direct observation. Yet, here's what I find beautiful and almost miraculous about this situation. Despite these boundaries, despite the unreachability of so much of the cosmos, we understand these places remarkably well. We can't visit the interior of a black hole, but we can write down the equations describing how space-time curves inside the event horizon. We can't travel to galaxies beyond our cosmic horizon, but we can calculate what's happening there based on the laws of physics, which we have every reason to believe are universal. We can't shrink down to the Planck scale, but we can infer its properties from quantum mechanics and general relativity. We can't survive inside a neutron star, but we can model its interior structure with impressive accuracy. We can't touch the sun's core, but we can detect neutrinos streaming from it and confirm our theories of nuclear fusion. We can't visit the Boeta's void in any meaningful sense, but we can map its extent and understand how it formed. Even white holes, hypothetical as they are, We can describe mathematically and analyze their properties. This is the power of science, the astonishing capability of the human mind to understand things it cannot directly experience. We're pattern recognizing machines, storytelling apes who evolved on the African savanna, and yet we've developed mathematics and physics to a level where we can comprehend the behavior of matter at temperatures of 15 million degrees, at densities 400 trillion times, that of lead at scales 10 to the power of 35 times smaller than an atom, at distances so vast that light takes hundreds of millions of years to cross them. We've built instruments that extend our senses across the electromagnetic spectrum, from radio waves to gamma rays. We've created theories that predict phenomena like gravitational waves and black hole shadows decades before we could observe them. We've learned to read the subtle clues the universe provides, the spectral lines from distant galaxies, the oscillations in a star's brightness, the slight wobble in a pulsar's rotation. And from these clues, we've reconstructed the history and structure of the cosmos with stunning accuracy. The boundaries we've explored tonight define what's unreachable, but they also define what's real. They're not arbitrary limitations imposed by our current technology or temporary gaps in our knowledge that will eventually be filled. They're fundamental features of reality itself, written into the laws of physics. The event horizon of a black hole isn't a barrier we'll someday engineer our way across. It's a consequence of how gravity and space-time work, as fundamental as the fact that effects follow causes, or that you can't travel faster than light. The cosmic horizon isn't a temporary limit of our telescopes that better instruments will overcome. It's a consequence of the expansion of space, and no matter how long we wait, or how powerful our telescopes become, those distant regions will remain forever beyond our view. The Planck length isn't a scale we'll eventually probe with more energetic particle accelerators. It's the resolution limit of space-time itself, where quantum uncertainty and gravitational effects become so intertwined that the very concept of distance breaks down. These boundaries are telling us something profound. Reality has an architecture. It's not infinitely complex in all directions. It's not arbitrary or chaotic. It has structure, organization, fundamental scales, and limits. There's a smallest meaningful length, the Planck length. There's a fastest possible speed, the speed of light. There's a maximum density matter can achieve before collapsing into a black hole. There's a boundary to how much of the universe we can ever observe set by the cosmic horizon. These aren't bugs in the design of reality. They're features. They're the rules of the game, the constraints within which everything that exists must operate. And within those constraints, what richness emerges. Think about it. The laws of physics, as far as we can tell, are the same everywhere in the observable universe, and have been the same throughout cosmic history, since shortly after the Big Bang. These laws are simple enough that we can write them down in equations filling just a few pages. And yet, from these simple universal laws, applied over billions of years, across billions of light years, has emerged the fantastic diversity and complexity we see around us. Stars and planets, galaxies and clusters, nebulae and supernovae, pulsars and quasars, molecules and minerals, atmosphere and oceans, and somehow, improbably, wonderfully life itself. Consciousness, intelligence, art and music and science and love. All of it arising from the same basic rules, the same fundamental particles, the same forces operating within the same boundaries. The unreachable places we've explored are extreme manifestations of these rules. Black holes show us what happens when gravity becomes so dominant that nothing else matters. Neutron stars reveal matter at its densest possible stable configuration. The sun's core demonstrates nuclear fusion at the scale that powers stars. The cosmic horizon shows us the consequences of universal expansion. The Planck scale reveals the quantum nature of reality itself. The Bioda's void illustrates how structure forms through gravitational attraction over cosmic time scales. Even hypothetical white holes, by their apparent absence, teach us something about time's arrow and the special initial conditions of our universe. Each unreachable place is like a laboratory experiment conducted by nature at scales and energies we could never reproduce, testing the laws of physics at their extremes and showing us what's possible, what's forbidden, what's required, what's inevitable. There's a philosophical question worth pondering as you drift towards sleep. If a place exists but can never be reached, can never be observed, can never affect us in any way, does it exist in any meaningful sense? We've discussed regions beyond the cosmic horizon that are causally disconnected from us. We've talked about the interior of black holes, from which no information can escape. These places, if they exist at all, exist in a separate reality, from ours divided by boundaries that even light cannot cross. Can we say they're real? Most physicists would answer yes. The laws of physics don't care about our ability to observe something. General relativity describes space-time everywhere, not just the parts we can see. Quantum mechanics governs the behavior of particles at the Planck scale, whether we can measure them or not. The galaxies beyond our cosmic horizon are just as real as the ones we can see. They're made of the same particles governed by the same forces existing in the same universe. The fact that the expansion of space has carried them beyond our ability to ever communicate with them doesn't make them any less real. Reality in this view is larger than observation. It's larger than experience. It exists independently of our knowledge of it. But there's another perspective worth considering. Some interpretations of quantum mechanics suggest that observation, measurement, and information play a fundamental role in defining what's real. In this view, things that cannot be observed even in principle occupy a strange ontological status. They might be real in the sense that the mathematics describing them is consistent, but they're not real in the sense of being part of our physical reality, our causal universe, our observable cosmos. The boundary between reachable and unreachable might also be a boundary between real and theoretical, between physics and metaphysics. I don't claim to have the answer to this question. Smarter people than me have debated it for decades without reaching consensus. But I think the question itself is valuable. It pushes us to think carefully about what we mean by real, about the relationship between observation and existence, about whether the universe exists independently of observers, or whether observation is somehow constitutive of reality. These are deep waters, and I won't pretend to navigate them definitively. But floating on the surface of these questions as you drift towards sleep might lead to interesting dreams. Let me share one final thought about why all this matters. Why spending time contemplating unreachable places is worthwhile rather than depressing or futile. In our everyday lives, we're surrounded by the reachable. We interact with objects we can touch, people we can talk to, places we can visit. We solve problems that have solutions. We achieve goals that are within our capability. And this is good and necessary. This is how we survive, how we thrive, how we build civilizations and create meaningful lives. But there's a danger in spending all our time with the reachable. We can start to believe that everything is solvable if we just work hard enough, that every question has an answer, if we're clever enough, that every boundary can be crossed with the right technology. We can lose sight of the fact that reality has limits, that some things are genuinely impossible, that the universe is larger and stranger than our ambitions. The unreachable places remind us of these limitations, and in doing so, they give context and meaning to what we can reach. Think of it this way. If you could go anywhere, if every place were accessible, if there were no boundaries or limits, would exploration mean anything? Would discovery have value? Part of what makes reaching a destination meaningful is that it's difficult, that it requires effort and ingenuity, that not every destination can be reached. The existence of unreachable places makes the reachable places special. The fact that we can't visit the interior of the sun makes our ability to understand it through neutrino detection and helioseismology all the more impressive. The fact that we can't travel to distant galaxies makes our ability to photograph them and measure their properties a genuine achievement. The limitations define the achievements. Moreover, the unreachable places inspire us to be creative about what reaching means. We can't physically visit a black hole interior, but we can detect the gravitational waves from merging black holes and extract information about their masses, spins, and the nature of space-time. We can't travel beyond the cosmic horizon, but we can study the cosmic microwave background and infer what the universe was like just after the Big Bang, gathering information from light that's been traveling toward us for nearly 14 billion years. We can't probe the Planck scale directly, but we can look for indirect effects in the behavior of particles at accessible energies. We've learned to reach the unreachable indirectly through inference and deduction, through creativity and cleverness, through the power of mathematical reasoning combined with careful observation. This is perhaps the deepest lesson of our journey tonight. The boundaries aren't complete barriers. They're challenges to be approached with different tools. When direct observation fails, we develop indirect methods. When experiments become impossible, we rely on theoretical modeling. When physics breaks down, we work to develop better theories. The unreachable doesn't mean unknowable. It means we have to be smarter, more creative, more patient. We have to accept that some questions will only be answered partially, that some mysteries will remain mysterious, that some boundaries will never be crossed. But within those limitations, there's still infinite room for discovery, for understanding, for the kind of knowledge that comes not from visiting a place, but from comprehending its nature. As you lie there in bed, your body relaxing, your breathing, slowing your mind, beginning to drift. Think about this. You are a collection of atoms that was once scattered across the cosmos. The calcium in your bones was forged in supernova explosions. The iron in your blood was created in the cores of massive stars. The oxygen you're breathing right now was produced by nuclear fusion in stellar interiors, much like the sun's core we explored tonight. You are quite literally made of stardust, assembled by 13.8 billion years of cosmic evolution, into a configuration complex enough to contemplate its own origins. And here you are, lying in bed on a small planet orbiting an ordinary star in one galaxy among billions, thinking about black holes and cosmic horizons, quantum foam and neutron stars, solar furnaces and cosmic voids and hypothetical white holes. You're contemplating places you can never visit, scales you can never directly perceive phenomena, you can never directly experience. And yet, through science, through mathematics, through the accumulated knowledge of thousands of researchers over centuries, you can understand these places. You can know them. You can hold in your mind accurate pictures of what exists in the most extreme corners of reality. That's extraordinary. That's miraculous. That's the gift that science gives us, the ability to transcend our limitations, to reach beyond our immediate sensory experience, to comprehend realities we cannot touch. The unreachable places are unreachable to our bodies, to our instruments, to our direct observation. But they're not unreachable to our minds. We can think about them, model them, understand them, incorporate them into our worldview. In a very real sense, by understanding these places, we've reached them after all, just not in the way a traveler reaches a destination, but in the way a mathematician reaches a truth through understanding rather than through presence. So, as you drift off to sleep tonight, carry with you this thought. You live in a universe vast beyond comprehension, strange beyond imagination, filled with wonders you can never visit but can still know. You're bounded by physics confined to a tiny bubble of space-time, limited by the speed of light and the expansion of space and the arrow of time and the resolution of reality at the Planck scale. And yet, within those boundaries, you're capable of understanding the whole, of grasping the structure, of comprehending the unreachable. You're a temporary arrangement of stardust that's become conscious, that's become curious, that's become capable of asking questions about the nature of existence and finding answers that are true, that correspond to reality, that give you knowledge of things you'll never directly experience. The universe has drawn boundaries around what you can reach, but it hasn't drawn boundaries around what you can understand. And that's the greatest gift of all, the freedom to explore infinity from within our limitations, to map the unreachable from the safety of the reachable, to know the unknowable through the power of reason and observation and imagination working together. Sleep well tonight, knowing that you're part of something vast and wonderful. The same laws that govern black holes and neutron stars govern the atoms in your body. The same expansion that carries distant galaxies beyond our horizon is happening in the space around you, though at such small scales you'd never notice. The same quantum uncertainty that makes the Planck scale fuzzy is present in every atom of your being. You're connected to these unreachable places not by proximity, but by physics, not by travel, but by shared rules, not by observation, but by comprehension. The universe is one thing, one system, one interconnected whole, governed by the same principles everywhere and at all times. And you remarkably are a part of that whole that has become aware of the whole, that has looked outward and inward and discovered both the vastness of space and the limits of what's knowable and found beauty in both. Thank you for joining me on this journey to the strangest, most unreachable places in the universe. I hope you've learned something new. I hope you felt a sense of wonder. And I hope as you drift off to sleep, your dreams will be filled with black holes and cosmic horizons, quantum foam, and neutron stars, nuclear furnaces, and cosmic voids, and perhaps even the mathematical ghosts of white holes that exist in equations but not in reality. The universe is strange and beautiful, vast and mysterious, and we are privileged to live in an era where we can understand so much of it, even the parts we can never reach. Until our next journey together, sleep peacefully, dream wildly, and remember, the boundaries of the possible define the shape of reality. But the boundaries of understanding are limited only by our curiosity and our courage to follow the evidence wherever it leads. Sweet dreams, star travelers. There are more cosmic mysteries waiting for us, more impossible places to explore, more boundaries to contemplate. But for now, rest well. The universe will still be here when you wake, vast and strange and full of wonders, both reachable and unreachable, both known and waiting to be discovered.